Hey, I just want to check
You are.
look at the presentations folder.
Yes.
Yeah.
So I just wanted to make sure, I guess,
It's too much up because Andy will have a coronary.
because it kind of has to be presented in with PowerPoint rather than through the Google, because it's a PowerPoint file.
Okay, I don't know. Okay, here. So let's.
Yes. Here I am.
Can we open? Okay, Thomas. We need to open that file. Oh, there it is.
Okay,
It just takes a while, so we might want to pre-open things.
Wish you guys had used box so that if it's in box, the load up is real. You
Yeah.
can close this.
Close the floor. Yeah.
Should I try going through it, or?
Just make it
Really
large.
quickly. Okay, now,
Mhm.
did we get the laser pointer where people can
this is
see it at home?
Okay, let's see. Yeah, there it is. Yeah. If you want, this is a mouse, and this goes. Yep. Yeah.
Okay.
That goes. Yeah. That
Awesome.
goes back. That goes forward, and that's.
Okay, awesome.
And the
And we have
laser
extra
pointer-
batteries, or you're going to be here, right?
Yes, I'll be.
Okay,
Yeah.
good, thank you.
Are you the first speaker?
First
no,
in-person
you-
speaker, but I'm number 2. So.
Yeah.
Ask all the speakers.
Awesome. Yeah, everything looks good. Yeah, I just want to make
You
sure.
can clip this somewhere around here.
Yeah, my talk isn't until, I guess,
What
11.
time?
11.
Yeah.
So we have time.
Hey, Katie.
So this is what your one is the same thing that the same link that I showed you, right?
Just wondering, no one else is joined.
Yeah, I know, that's why.
That's what I'm wondering.
I was gonna, Thomas said it too, sorry. Sent us an email with it, but I don't know. Okay.
It's been years. Maybe she could sing, that's what I was thinking.
Yes.
She doesn't sing
That's-
for long.
But
1 2 1 2 1 2 1 2. Yeah, green is on.
well, wait, so you don't want.
Because some people like to move.
Okay, so and you're
Yes. But the main speaker I'll have you.
Oh, good, Mark's here. Yes. Yes. We got a couple minutes. Oh, yeah, Bill heard people right now. Well, we got, yeah, just about, we got.
But I didn't bring it, I forgot. Yes. Let's see.
Recognize everyone from their pictures, even with their masks.
It's better than me. Okay.
My phone. Some people can't do that. Some people are really
Andy, Can we close some of these windows that we don't actually need? So I put, just so you know, so David Martin, that's his, and Goodmunders, that's his.
Okay.
They're both in the first science session. I don't know
Okay.
who the third person is.
Oh, who's chairing the first science session?
I don't know.
The,
I sent it out. I don't have a.
Goodmunder must know.
Who's chairing the first science?
This meeting is being broadcast on Facebook Live.
Wait, Facebook. I thought we were doing YouTube.
What? What did you just hear?
I heard something that said something about Facebook Live. We're doing YouTube though, right?
Yes, I think so. Where is our AV person?
They're in the booth.
Oh, in the booth.
Andy, do we need this open?
No. Oh, you're so nice and tidy.
I get confused easily when I'm flustered because I was on the other end when we were doing the.
Right.
You're gonna be on the.
Right, but he was going to show me how to do the switching.
Yeah. Yes, I am.
Bring our next chair. Who's our next chair? Megan. We should show Megan too. Megan should see this too. Megan, join us for a second. Hi, and this is our AV person. So Thomas, if we're set up now. Just switch back and forth between virtual. Why don't you show us? So right now we would be basically in person, right?
Yeah.
So here's a directory with all the different talks. This is the directory. So you just click on them and it'll come up and yeah.
Not sharing.
Right? Presentation.
Kevin, do you see the screen share?
Is here and Goodmunders is there. Okay. So
It's not being shared?
those, and I think maybe there's a virtual in addition.
Yeah, there's one more version.
Sorry, you're not even sharing right now. I think you'd stop sharing. Let me go to Blue Jeans.
Okay.
Is the first speaker, who's sharing first? Are you going to share or is it remote?
The first speaker's you,
Right. The first speaker is me,
All
and
right,
then
so
it's,
then remote, and then in person.
well, so it's first speaker is me, and then we have Nancy, and then we have Mark
Okay.
Clampin, who's
Let me
remote.
share the screen. Okay, so now it's been shared. Then you can bring up your slides.
So you have it. Okay, good. So it's mirrored right now.
You will know when you open the slides.
Okay. Now you open the slide. Okay.
But it is mirrored because you're seeing it here as well.
Okay, but that's. Oh, I see. It's not. Yeah. So it's mirrored until you open the slide. Super. That's.
No, let's see if you just open the slide. I'm just curious to see what it's going to do because
That's
Yeah.
perfect. Yep. And let's try David Martin's just to try one that's not. Let's try Keynote. Yeah, it's just you're not getting the notes. But
okay. Give me 1 second to go start the recording. And
yeah. So and it's YouTube, right? It's something.
it's YouTube. Just to let you know, you can either use this or you can use a handheld.
Oh, yeah, I can do
So can you please ask all the speakers to use
use that.
yes.
Okay. Nancy, do you want to use the lanyard? Okay. All right. So I'll do the beginning. And then,
Okay, so I can just go.
yeah, so I'll do through the leads, and then so first we're having Nancy Levitin, who's the director. Then we're going to have Mark Clampton, who's the daughter, and then we're going to have and then we're going to have Mark Clampton. Then we're going to have the leads. Then we'll go into the science session.
Just leaving this up because the Wi-Fi is there.
Okay, where's Jennifer Wiseman? Saw her a minute ago. I know because I wanted to introduce her too.
Way in the back there.
Wait, that's typical. Where? Which one?
Walking down.
Oh yeah, there she is. Oh, okay. Yeah, she's not. She doesn't hog the limelight. Okay, there she is. Okay. Yeah, we're sharing. Okay, we're 2 minutes past the hour. I guess. So, welcome everyone. This is really a special treat. We're all here in person, though covered with cloth, and it's great to see almost all of you in the room, and quite a few, and the rest of you almost all online. So this is fantastic. We had one meeting of the fellows in 2019 before the pandemic, and then after that, it was for the past 2 years, it has been virtual. And so we're glad to have many of you here in person at Space Telescope. I'm Andy Fruchter. I'm the Hubble lead, and I'm based at Space Telescope. With me here today are John Gelino, who's the Sagan lead at Caltech. Hey, Dawn. And there'll be Dawn and Paul, and there's Paul Green. He's at CFA. He's the Einstein lead, and Katie Alatalo, the deputy Hubble lead here at Space Telescope. They'll be all making a after you hear the introductory welcomes. They'll be making a presentation telling you all about about this meeting. Okay. So we're going to have a couple of talks today. First, from the director of Space Telescope, Nancy Levinson.
Thank you so much, Andy, and thank you all for participating, whether you're here in person or here virtually. This is always just such an exciting week for us, and so at Space Telescope Science Institute, we're really pleased to be able to support this really exciting symposium. What I hope some of what you'll get out of this week is a real opportunity to interact with each other. And also to intellectually challenge each other, that you're coming from different areas of interest with different ideas, and so that this should be a very stimulating week that you have to work with each other. One of the really exciting things about this whole fellowship program is the independence that you have. That you are able to explore and push the boundaries in whatever interesting directions you identify and you find are worth pursuing. And so that just makes it so exciting for all of us who get to listen to your talks and listen to some of your results, and also to have some of those conversations with you to learn that way. This is a really strong cohort of people, and you are bringing those different strengths. You're bringing lots of diverse expertise, whether you rely primarily on observations or theory, or use technical approaches to advance science. Again, it's that real mix of different approaches and different ideas that can be so strong. And so this is a real opportunity to learn from each other. Again, whether you're here in person, and some of that will happen over coffee, or also whether you're participating remotely. I think a little bit about where we are today, where we are in September 2022, and how some of that is a bit different from a year ago or several years ago. One of the things that's different, certainly for us at the Institute, we're very aware of, is that JWST has launched and is successfully operating. And so that's just really giving us incredible new opportunities. That JWST is delivering on its promise. It is functioning as we expect. And so we're getting all kinds of amazing observations of the entire universe, whether it's a question of what's happening in the solar system or looking at the universe as a whole. And so what we do expect using this great new facility, as we often find with these great observatories, is not only do we answer some of the questions that we have, but we begin to ask new questions. And that's really exciting, asking those questions that right now we don't even know that exist. Today, also looking back over the last few years, we're in a different position, in an advanced position of using some new techniques and new approaches to how we study astronomy. We really are relying on multi-messenger astrophysics. We really are deeply using the information about the time domain that we didn't have before. We have new computational facilities that let us do things that weren't previously possible. And we also have increased accessible archives, so we can really build on so much of what's happened in the past and don't have to recreate all of it anew every time. Another really important change today is that we are after the latest release of the Astronomy and Astrophysics Decadal Survey, Pathways to Discovery. And so that decadal survey set out our aspirations as a community, our aspirations for astrophysics. One of the really exciting aspects of this most recent decadal survey is that it also looked at the state of the profession. How do we engage in science? How do we participate in that human activity? And that's another area where I know that you as fellows are very much pushing us forward, leading the community to do science well in all aspects of that. Of course, another exciting thing for me that came out of the decadal survey is looking forward to new missions and new capabilities. In particular, looking ahead at the new great observatories, the next generation of flagships. That your fellowships are based on the original great observatories, and that multi-wavelength, multifaceted approach has really helped us advance science. And so I'm very much looking forward to being able to do that with the next generation, again, taking that multi-wavelength and multifaceted approach. And so I'm looking very much to you, the generation who will be defining the questions that we need to answer with these new facilities and setting the requirements for them so that we do exciting science. And you, of course, are very much going to be part of that user base to make those a reality in the present day. So I'm looking forward overall to an exciting week, hearing about the research that you're doing, hearing about the exciting discoveries that you have made. I'll try to join you for much of that. And I will stop there and hand it back to Andy.
Okay, thank you very much, Nancy. Now we're going to move to NASA, and we have in-house with us the senior project scientist for HST, Jennifer Wiseman. We didn't expect Jennifer would be able to make it, but she did, so I just want to introduce you to her. Jennifer was a Hubble Fellow, yes, so as were many people in the room. So we were, so we're glad to have both former and present fellows here. But we're going to go online to Mark Clampin, who is the new Director of Astrophysics at NASA headquarters. Mark, are you there?
I'm here. Can you hear me?
Okay, there, I see you now. Right, so I'm going to stop sharing here, and then you go to the top of your screen, and a little screen should appear that says Share Screen, and if you want to share your screen, you can do that, but we can see you just fine right now. Go in the blue G, if you can see me in the window where you see me, go to the top of that, and a few little circles should appear, and one of them looks like it has got a screen in it, and click that.
So, Andy, can you hear me?
Yes.
Okay, I cannot share my screen because I'm on the browser and not using the application.
Oh, right. In NASA, you'd have to get someone to come and give you permission. So,
Indeed.
Right. Yeah. I will turn. But we get you. Let me just. Let's see. How do we get you? Okay, escape. You get my blue jeans up. And let me see. Mark, why don't you just start? Let's see. Why am I? This was set up by. Let's see. How do I get that to be in? I want to make that the main window. Where is Thomas? Let me try. Yeah, Penny, I don't think will be large enough. Oh, there he goes. It does. Okay, there it is. It's a little bit blurry, but there he goes. Okay, is that good? Yeah. Okay. Mark, why don't you try talking now?
Okay, I'm here.
Is that good? All right. Please go ahead.
Okay, so thank you, Andy. I really appreciate the introduction. So as Andy said, I am Dr. Mark Clampin. I just started at NASA headquarters as the new director of the Science Mission Directorate's Astrophysics program, and I'm following on from the sort of 10 years plus of great work done by Dr. Paul Hertz. So it's my really great pleasure to welcome everybody today and also to congratulate the new fellows amongst you. Thank you for participating in this meeting. I think, Nancy touched on this. Scientific interaction has really changed as we work in this new hybrid format. So I really encourage you to make the most of this meeting because these scientific interactions are extremely valuable and a key part of the fellow program. This is really a tremendous program that presents unique opportunities. And as you can see from the success of the alumni in this program throughout our community, it provides really a lot of opportunities. And as Andy pointed out, our own Jennifer Wiseman's a former alumnus. This is a really great time to be working in astrophysics. We've just had the launch of the JWST, and that mission is starting to prove really successful. As of yesterday, I was preparing a presentation for the Hill tomorrow, and it looks like we have something like 100 papers already submitted and on AstroPH addressing early release science and some of the early release programs that are out there for the science community. So I think, one of the things that I see JWST demonstrating is one that when you have a new capability, you can bring about major new discoveries, and even from the early release science, that's pretty astounding. And I'm sure some of you are actually engaged in working with these JW observations. I think the other thing that the early release science program is also showing, though, is the value of open science and the fact that it allows a larger component of our community to get engaged in these missions at a very early stage and see how the data looks, try different capabilities so that they can write stronger and more compelling proposals as the next cycle comes around. I also want to just mention, that we have a lot of other new opportunities in astrophysics coming up. So next year we will issue an announcement of opportunity for the very first astrophysics probe. This is a new mission line recommended by the Decadal Survey. We're also starting to work with our partners in the NSF and the Department of Energy to formulate a time domain and multi-messenger science program where we are really working across the full TDAM community. And as Nancy also mentioned, we're starting to look at developing the technical maturation program for the next large flagship that was recommended by the Decadal Survey. So that's going to be a really exciting activity for the next couple of years. So I just wanted to finish up by saying that my colleagues at headquarters and Goddard are present at this meeting, and they wanted to let you know that they're really here to provide you, the fellows, with any assistance that you may need. First and foremost, our job is to help you have a successful and rewarding experience. So please don't hesitate to reach out if you need something. And with that, I will say thank you, congratulations, and welcome again. And I'm looking forward to some of the science presentations this week. And I will hand back to Andy. Andy.
Thank you very much, Mark. It's great. Mark was at Space Telescope before he moved to Goddard and to help be one of the main builders of JWST. So I think we should give a round of applause for that as well. Thanks, Mark.
Thank you.
Pat, we also have Pat Knezik online. Pat is the project scientist for the NHFP at Goddard. And there she is. Pat, do you just want to say hello for a moment? I can.
Yeah, I'll just say hi. Welcome, everyone. I'm absolutely delighted to see all of you here. I wish I could be there in person to join you, and I can't wait to hear about the exciting science you're all doing. Thanks so much for coming together, and I look forward to a really, really productive week. Thanks.
Thank you. Let's see. Now I got to understand. Okay. Escape. Let's see. Back to it. Okay. Now we're going to have Dawn Gelino come up and start the leads presentation on all the rules and regulations and the fun we're going to have.
We are going to have fun. All right, let me just find it though. There it is. No, it's right here. Wait, but then I have to share, which nobody showed me how to do.
Let's go back to the blue jeans. Okay. So this one.
Okay.
Okay, you try. I'll just do. Okay. Yeah, let's just see how this goes. Go.
I think we're good. Yeah, I can.
Yeah.
Yep. All good. Thomas, yes. Thomas is our IT guy. He's gonna keep things working this week. Yes.
So that can shoot.
Yeah.
Okay, and now the slideshow.
Where?
Yeah.
Okay. Okay, he'll take care of unpinning. Hopefully I'm using the right. Maybe not. Works. But the. All right, well, we'll figure out the pointer later. I don't really need a pointer, though. All right, good morning, everybody, or good afternoon, good evening, wherever you are online. My name is Dawn Gelino. I'm the Deputy Director for the NASA Exoplanet Science Institute, or NEXI. As Andy mentioned, I'm the Sagan lead. We lead this program by committee. It actually works pretty well, which is great. I'm so happy to see everybody here. And those of you who are online, although we can't see your faces, you can turn your cameras on, I think. I want to remind people, if they're comfortable, they can take off their masks. I actually just had COVID, so I feel kind of invincible at the moment. I know that won't last very long, though. So when you're speaking, you can take off your mask if you want to, but you don't have to. Everybody just be at your own comfort level. Okay, so thank you all for coming. This is, as also Andy mentioned, this is our fourth symposium with the merged program, the Sagan, the Hubble, and the Einstein program merged. This is the first time we've done it hybrid. Hopefully everything will work seamlessly. Off to a decent start. So we all know that these are still really difficult times, right? The pandemic is not over. COVID is still with us, as evidenced, everybody with masks on. So thank you, for those of you that could make it. We hope those of you that could not make it because you're not feeling well, feel better. I will get to the COVID policies in a minute for this meeting. So thank you for your flexibility and your patience. We are looking forward to just wonderful talks. This is like the highlight of my year. I get to learn so much when we have these symposia. But we also have non-science sessions. So this afternoon we have Sharon Gatling from Space Telescope will come and lead a DEIA session here, and that's for if you're part of the public community and watching online, these non-science sessions are for the fellows only. So we'll have that session this afternoon. On Wednesday, we have the grants folks coming, and they will be here to answer your benefits questions or policy questions. So think about it, both, those of you online and in the room, think about questions that you have. And a lot of new ideas and policy changes come from this particular session. So, don't be shy, ask. Or if you need clarifications or anything like that. We have a careers panel that a few of the fellows have put together, And so you'll be able to hear from people in different parts of the community. And then on Friday, we have the very popular open mic session that we've had for, I think this is the third time we've done it now. We started it when we had, went virtual with these symposia, and it's actually, it's a lot of fun. And so there'll be more information about that on how to sign up for that coming up. Okay, code of conduct. We are all adults in this room. We are all adults online. Let's act like adults. Let's behave professionally. We will not tolerate any harassment or any harassment of participants in any form. I have no problem yelling at people if I have to. So all communication should be appropriate, for a professional audience. Remember, if you have critiques, you critique the ideas, not the people themselves. And if you want to share photos or content from the meeting, please get permission from the people that you want to share the information about. We'll ask you to stop if we have to, and you're expected to stop whatever you're doing to comply immediately. And if you see something that makes you uncomfortable, or you need to report a violation, come talk to any of the leads, myself, Andy, Paul, or Katie, and we'd be happy to see what the next steps are. But hopefully we won't have to enact any of this. Okay, COVID protocols. So we're asking everybody to wear medical grade masks inside the meeting venue. I see those here, which is great. We do have KN95 masks at the registration desk if you need one. There are also COVID tests. We didn't actually bring any in here, did we? There are COVID tests at the registration desk if you did not get one this morning when you got your badge. Okay, Andy's got one right there. If you didn't get one when you got your badge this morning, feel free to pick one up there. We do ask that people test the morning before in your hotel room before you come. If you're not feeling well, please don't come. We do have the Blue Jeans link, and you can watch from your hotel room. So please do that. And we'll be eating together, and so we won't have masks on while we're eating, obviously. And if you haven't already tested this morning, please do so. And I think with that, I am passing off to Katie. You want to, or I can keep going? Up to you. Okay, I'll keep going. All right. So this is a hybrid meeting, and even when it was just virtual, it takes a whole team to put this together. We've already introduced the 4 leads. And then we have Marcel, who's sitting here. He's helped to keep us on track for the last few months. We have a new NHRP project manager. And we have back at Caltech, part of my team at Caltech, Megan Crane. She's our program assistant and lead programmer. And then there's the events team here, Flory Hill, who is at the registration desk this morning. There's Sharita, who's also, I believe, out there, and Darlene Spencer. And so if you have logistical questions about here, ask them. And then we have Thomas, who you've seen several times, who is our AV and internet guru, and we thank him for helping us test and all the help he's going to give us this week. We'd also like to thank the Symposium SOC. The fellows this year took on a good part of the burden of putting together the science program and the career panel, and so we would like to recognize all the work they've done. They've made our lives significantly easier. Yes, thank you. Okay, and with that, I'm going to hand over to Paul, and he's going to finish. We have a few more slides.
Thanks. Yeah, great to see everybody here today. It's so much fun every time, and I'm always blown away by the talks, so I'm looking forward to this. We know it's a big challenge to go from sort of 200 level astrophysics all the way to the newest part of your research in 12 minutes. But you always do a great job. So we're all psyched about that. So please do make sure your presentations are uploaded the day before your presentation, just so we can check that everything's there and we don't have to kind of run around in a panic in the morning. And as you know, remote speakers should submit a video to that Google folder, just in case there's trouble, technical issues or connection issues. So yeah, the presentations are all 12 minutes, plus 3 minutes for questions and transitions. And if we do have a big timer here with huge white letters that will be intimidatingly ticking down as you speak. For the remote presenters, please, yeah, keep your mic muted so we don't hear random noise coming through. If you don't manage to get a video up there, we can always do your presentation by you telling us next slide, please, and then we'll click forward. And if you're remote, you can please type any questions into the Blue Jeans chat. And if you're not a fellow, but you're watching on the YouTube channel, you can ask questions by typing into the YouTube comments. And then the nice thing about Slack and having the Slack channel, as you all know, what much better than me, is that after a talk is over, you can chat about it. You can leave questions. You can discuss in the Slack channel. This whole thing is being recorded. Just if you're uncomfortable with having your talk be publicly available as a video, just email us at nhfp@stsci.edu, and we can make sure it's not there. But you will have the opportunity to then pull your talk off of the stream if you want to use it for something. So yeah, the open mic is happening it's the very last session on Friday from 4 to 5:15 p.m. So you can do anything you want as long as it's not science, because we will have been hearing about science all week long. It's a chance for us to get to know something interesting or quirky or fun about your life or about your concerns about the world or about education or public outreach. If you want to do a performance of some kind, that's great. The maximum is 10 minutes. So you can already sign up. I see that I'm the only person signed up there so far, so that's really not good. I encourage you to sign up for things, because if you don't, I have a whole bunch of songs from junior high school that I'm going to perform. So you have the link in Slack, and I believe in an email also to go and sign up on the sheet. Or you can email us with your descriptive title and your estimated length by Wednesday, because then I'll put together the program. Otherwise, we get the exciting opportunity to go and look at the JWST Missions Operations Center, the MOC. And we've been assigned to tours alphabetically, I think 8 at a time. 6? Okay, 6 people at a time. And it takes about 15 minutes. And so we'll let you know who is signed up each day before lunch. Tuesday afternoon is free. And we will, if you haven't been to Baltimore before, we will get you a list of cool things to do as options for your free time. And then Wednesday, we have a banquet symposium dinner, 6 p.m. at Gertrude's, and that should be fun. And that's it for the Leeds presentation. Oh, we're going to have that's right, we're going to do a group photo. But we don't know exactly when. But yeah. And then we can start our official program, right? So who's the first chair? Great.
Yeah. Oh, yeah, I think it's working. Okay. Okay. Yeah, so our first science talks are going to be planet formation. I think our first one is online. So, David, if you are there, if you want to share your screen.
Sure. Just double checking my microphone works. You can hear me all fine?
Yep, we can hear you.
Video is good?
Yeah, I can see you. I don't see your slides yet.
Okay.
But I can.
Is this still pinned here? This may still be.
I can pin him
There we
instead.
are. There we go.
How's that good? Slide look good?
Good. Let's just do full screen.
Okay, perfect. All right, cool. So our first talk is going to be David Martin from Ohio State University, who's going to be talking about. Sorry. Oh, are we just going to hang out then for a bit, or?
All good?
Okay, we'll take a 10-minute break. Okay, I guess we'll be back in 10 minutes, David.
Oh, okay, sure.
Questions from this morning?
A quick open mic.
Yeah, we can do that.
Let's go around and stand up and say your name and what.
Wait, somebody.
Yeah, we're going to do
Introductions in the intervening 10 minutes before we officially begin. And so, yeah, we'll pass around a mic and just say your name and your what year of NHFP fellow you are and what institute you're at, and then do a little dance.
Okay. Okay, so you already heard who I am, but my name is Jennifer Wiseman. I'm the senior project scientist for the Hubble Space Telescope mission at NASA Goddard Space Flight Center, and we are all really excited about your fellowships and interested in hearing what you're doing. And there are a lot of scientists at NASA who are, not to intimidate you, but who are watching on the YouTube channel because they're very interested in hearing what's going on in this forefront science. I was once a Hubble Fellow. I gave a talk here just like you're doing, and it was really scary and intimidating, so I hope you don't feel that way. Have a good time. Here you go.
Thank you. So my name is Guðmundur Stefánsson. I'm incoming Sagan Fellow at Princeton, and I do exoplanets, and I'm excited to be here and chat with everyone.
Remove their masks for this if you feel comfortable.
Hi, I'm Melinda Soros Furtado. I'm a Hubble Fellow at the University of Wisconsin-Madison. I work on stars and planets. Happy to be here.
Hi, I'm Viraj Pandya. I'm a 2021 Hubble Fellow at Columbia. I mainly develop models of galaxy formation.
Applause, a very brief applause after everyone.
Hi, I'm Megan Mansfield. I'm a second-year Sagan Fellow at University of Arizona, and I do spectroscopic exoplanet observations.
Hi, everyone. I'm Mike Zevin. I'm a 2020 Hubble Fellow, and I'm at University of Chicago, and I do work in gravitational wave astrophysics and compact objects.
Hi, I'm Kishore Dev. I'm now starting my second year as an Einstein Fellow at MIT. I work on things that go boom in the sky with a focus on binary stars and what they do during mass transfer, and happy to be here.
All right. Hi, everyone. I'm Marcia Bryan. I'm a Sagan Fellow at UC Berkeley, starting my second year, and I think a lot about planet formation.
Hi, everyone. I'm Mike Wong. I'm a new Sagan Fellow just down south in DC at the Carnegie Earth and Planets Laboratory. I mainly study atmospheric chemistry of planets in the solar system and exoplanets as well. And on Friday, you'll be hearing about how I'm thinking about using atmospheric chemical networks as a new way for looking for life in the universe.
Hi everyone, my name is Eli Saidi. I just started my Hubble Fellowship at Michigan State University. I do multi-wavelength observations of stuff that go boom in the sky, like usually.
Hi everyone, I'm Shani Danieli. I'm from Princeton. It's really challenging to stand in the middle, so I'm just gonna. I'm starting my third year. I work on observations of galaxies, global clusters, and thinking about dark matter.
Hi, I'm a 2021 Hubble Fellow at Princeton. My name is Thales Gutke, and I develop ultra-high resolution galaxy simulations of dwarfs.
Hi, I'm Mike Grudich. I'm a second-year Hubble Fellow at Carnegie Observatories, and I like numerical simulations, numerical methods, mainly with applications to star formation simulations.
Hello everyone, I'm Ryan MacDonald. I'm a new Sagan Fellow at the University of Michigan, and I work on models of exoplanet atmospheres.
Hello everyone, I'm Jake Turner. I'm at Cornell University. I'm second year Sagan Fellow, and I work on exoplanet magnetic fields.
Hi everyone, my name is Luis Welbanks. This was not planned. We're the exoplanet contingent apparently. I work also on exoplanet atmospheres, and I'm excited to talk to everyone, especially those that make things go boom and dark matter, because I want to finally understand what that is. I'm at ASU, Arizona State University.
Hi everyone, my name is Erica Holmbeck. I am a 2021 Hubble Fellow, also at Carnegie Observatories. I kind of study things that go boom. So I study basically the origin of the heaviest elements. I use spectroscopy of metal poor stars, and I also run nucleosynthesis simulations.
Hello, everybody. My name is Ryan Sanders. I am a 2020 Hubble Fellow at UC Davis, and I study observational galaxy evolution, mainly with spectroscopy and galaxy chemical abundances, and the things I study do not go boom.
Hello, everyone. My name is Feng Long. I'm a new Sagan Fellow at the University of Arizona. I'm studying planet formation by looking at their forming environments.
Hi, my name is Sebastian Hoffert. I'm a 2019 Hubble Fellow, so I'm almost at the end of my fellowship. And I work on instrumentation for direct imaging of exoplanets. I'm also at the University of Arizona.
Hi everyone, my name is Emil Bohr. I'm a 2020 Sagan Fellow. I mainly do research also on instrumentation for high contrast imaging, mainly chronography and wafer sensing.
Hi everyone, my name is Anwar Shojib. I'm at University of Chicago, and I'm a 2021 Einstein Fellow. I work on cosmology and galaxy evolution using strong lensing.
Hi everyone, my name is Ariana Long. I am an incoming fellow at UT Austin, Hubble Fellow. I study massive galaxy evolution in the first couple billion years, the embodiment of living fast and dying young, and what that means for their baryonic and non-baryonic components. I'll also be walking over to a coffee shop during the coffee break for better coffee. No shade, Space Telescope, I'm sorry. So if anyone wants to join me, it's a quick 9-ish minute walk, so we have to leave right at the break.
Hi everyone, I'm Jessica Ava-Zabrowski. I am an incoming Einstein Fellow at University of Chicago, and I'm really interested in building new telescopes to try to study cosmology using line intensity mapping. So for the next few years, I'll be in some basement at University of Chicago building a telescope. And dear God, I hope it does not go boom.
I am Robert Williams, Osterbrock Professor at University of California, Santa Cruz, former director of this institute. At a time of spherical aberration and then its repair. And I cannot tell you how pleased I am to see the health of this program. I'll never forget the time, the first year of my directorship, when I was reporting to the Institute Council, and there was a distinguished professor who said, "Why are we wasting our money on this fellowship program when it's difficult to get jobs?" And of course, we fought for the continuation of that program, and I cannot tell you how healthy it is at this time. So a pleasure to hear these talks and be a part of this program.
Hi, I'm Alexandra Kuznetsova. I'm a 2020 Sagan Fellow. This is my last year, and I work on basically theory of star and planet formation, particularly how they might be connected and quite important.
Hi, everyone. I'm Mark from the University of Hawaii. I am a 2020 Hubble Fellow, and my work deals with observational astroseismology, stellar evolution, and galactic archaeology.
Hi everyone, I'm Joel Ong. I'm a new Hubble Fellow also at University of Hawaii, and I study the insides of evolved stars using astroseismology. Yeah.
Hi everyone, my name is Fei Dai. I'm currently working at Caltech to study the most extreme least habitable exoplanets. My talk is on Friday.
Hi everyone, my name is Sarah Izone. I'm a 2021 Einstein Fellow, and I work on radio observations of supermassive black holes and the Event Horizon Telescope.
Hey everyone, my name's Thankful Cromarty. I'm a 2020 Einstein Fellow at Cornell, and I work on millisecond pulsar timing for gravitational wave detection.
Hi everyone, I'm Xinyu Chen, and I'm a 2020 Einstein Fellow at MIT, and I work on gravitational wave astrophysics and cosmology.
Hello everyone, I'm Sultan Hassan. I'm incoming Hubble Fellow in the Princeton University. I'm mainly interested in reionization and galaxy formation, high redshift, but I also think more about how to extract information from observation, so I do lots of machine learning stuff too.
Hello, I'm Xiao Xu. I'm 2020 and also 2017 Hubble Fellow. I'm now at IS, and this is my last year. I work on MHD turbulence and cosmic rays.
Hello everyone, I'm Pradeep Gatkine, and I'm a 2021 Hubble Fellow at Caltech, and I work on developing astronomical spectrographs but on a chip. So I'll be showing some of those chips in my talk, which is on Friday morning, so please do come.
Hey everyone, I'm David Jones. I'm a 2020 Einstein Fellow at UC Santa Cruz. I work on supernovae, which go boom, as we've heard, and cosmology.
Hi everyone, I'm Misha Ivanov from the Institute for Advanced Study Princeton. I work on large-scale structure cosmology. I'm a second-year Einstein Fellow.
So hello everyone, my name is Hui Li. I'm actually very happy that Sebastian is here, so that I'm not the only 2019 Hubble Fellow. I've been working at Columbia for the last 2 years, and both working on numerical simulations of galaxy formation and star formation.
Hi everyone, my name is Tarane Eftekari. I'm a new Einstein Fellow at Northwestern. I also work on things that go boom with a focus on radio and millimeter observations.
Hello everyone, my name is Katherine Zucker. I am a second-year Hubble Fellow here at the Space Telescope Science Institutes, and I map the structure and dynamics of the Milky Way to better understand star formation.
And rounding it out, I'm Neil Reed. I am not a Hubble Fellow. I'm Associate Director of Science here. I did write the book on M-dwarfs with one of the first Hubble Fellows, Suzanne Hawley.
Okay, but actually, easier like that. We still have people online. We've got a few people online who maybe could turn on their cameras. Raluca, you want to do that? You there?
Or at least unmute.
Hey, I'm Raluca Rufu. I'm from Southwest Research Institute. I'm a 2021 Sagan Fellow, and I study formation of exoplanetary systems that are compact.
And Haley?
Hi everyone, my name's Haley. I'm an incoming Einstein Fellow. You're going to be starting at the University of Chicago in a couple of months. I work in simulations of large-scale structure formation in cosmology using numerical relativity. So come to my talk on Thursday to hear more about that. I'm really sorry I can't be there. I'd love to meet all of you in person, so hopefully next year.
Great. Darindu?
Hi everyone, I'm Tarindu. I'm an incoming first year Hubble Fellow at UC Berkeley. I study non-interaction compared object binaries and all things to do with time domain astronomy. It's nice to meet you all.
Thanks, Tarindu. And Thomas M is Thomas Marufu, who's in the AV booth over there. Who'll be back out in a minute, hopefully. And then Zoe. Think about Zoe Todd. No response. We'll go to Catherine. Catherine Nugent. Hi, Catherine.
Hi, I'm Catherine Nugent, and I am a first-year Hubble Fellow starting at Harvard, and I work on observations of massive stars.
Great. We have Kevin Wagner.
Kevin? Hey everyone, I'm a 2020 second fellow at University of Arizona. I work on exoplanet imaging, and I'll be talking in about a half hour, so I'll tell you more about that then.
Great. And Sinclair Manning? There's Sinclair. Hey, Sinclair.
Hi, everyone. I'm Sinclair. Unfortunately, my first bout of COVID was not as well timed as Dawn, so if my voice sounds funny, that's why. So sorry I can't be there in person. I'm a second-year Hubble Fellow at the University of Massachusetts at Amherst, working on optically and near-infrared dark, dusty star-forming galaxies at redshift greater than 3. Looking forward to hearing all your talks.
Okay, get well. Rohan, how are you doing?
Today is a good day. My name is Rohan Naidu. I'm an incoming Hubble Fellow at MIT. I'm very excited to study very early galaxy evolution, both by looking at ancient galaxies that have been integrated into the Milky Way, and also by searching for them at very high redshift, using JWST, which thankfully did not go boom. And you'll hear more about that later today. So excited to hear everything everyone's been up to.
Okay, great. And Tom, tell us the best way to pronounce your last name. Tom.
Yeah, I'm Tom Holoin. I'm a 2020 Einstein Fellow at Carnegie Observatories. I also study things that go boom, particularly tidal disruption events and supernovae. Apologies if you hear my son there. I will be there in person on Wednesday to give my talk, so I'll be seeing you all in a couple of days, but I couldn't be there right now to start the week, so see you soon.
Thanks, Tom. And then Andy Attack actually is joining us. Andy is at Project Science St. Goddard.
Hello. Yeah, I'm online.
Hey, welcome.
Yeah, sorry, I can't turn my camera on. I'm using my phone.
Oh, that's right. Yeah. And Mike, you're on online both here in it, right? So good. That's good. So we've seen you. And Jane Wang, are you there? Hey, Jane. We can't hear you.
Sorry, I'm in a room with other people, so I can't talk, but hello, everyone.
Hello. And then Dawn. So now we're back to David Martin, who's our first talk. So David, we'll go and see if we can get your talk up here.
Awesome.
So why don't you, let me see, I'm not sharing, so you just share your screen. Yep, there it is. Okay, and I will go turn this. All right.
All good.
Let's take it away.
That's good. Thank you very much. Thank you very much for having me. I'm David. This is Stanley. So, circumbinary planets orbiting two stars, are one of the most miraculous discoveries we've had over the past decade or so. Not only are there these cute exotic beasts, but actually they really tell us a lot about planet formation. They tell us about planet formation because we're really probing planet formation at the extreme, at the edge of what we believe is possible. And so whilst Kepler did an amazing job, it did only find about a dozen of these planets. Furthermore, TESS has added a couple, but TESS is not really designed perfectly for circumbinary planets. It's an amazing instrument, but it's not an optimal design for finding circumbinary planets. So what this leads to is we've got this quite biased and limited sample. There are a few problems, three of which I'm going to point out here. One is that all of the known planets around binaries are gas giants. There are no small planets around binaries, whereas around single stars, most planets are small. Another problem is that all of the known planets are coplanar, meaning that the planet and binary orbits are neatly aligned like a pancake or like the solar system. And finally, transits probe planets as a function of radius, whereas one would argue that mass is a more fundamental parameter. So through my work and some amazing work with my collaborators, there has been a few solutions provided. One, indeed, the fact that there are only gas giants we believe we can solve using this new Stanley algorithm which we've developed. This is something which I talked about at the last Hubble Symposium and also at Exoplanets 4. I will not be covering it today, but I will never avoid the opportunity to show a picture of my dog. What I will cover more today is the idea that maybe we don't even need to see the planets transiting. We can actually overcome this coplanarity barrier by looking at another method, a method of eclipse timing variations. And finally, to overcome this issue of not probing planets as a function of mass, we can actually go back to the original exoplanet method, and that is radial velocities. So today, I'm indeed going to focus on non-transiting circumbinary planets. My name is David Martin from The Ohio State University, and a lot of the work I'll be presenting today is led by some wonderful students who I've had the privilege of working with. Starting with eclipse timing variations. Now, a lot of you may have heard of transit timing variations, or TTVs. And indeed, in circumbinary planets, you have very large TTVs. The main cause of that is that the two stars are moving, and so the planet has to transit in front of a moving target. This imposes TTVs on the planet on the order of days or even weeks. Huge TTVs, the biggest we've ever seen. Now, this poses challenges for finding transiting planets, and that's not something I'm going to go into. What I will go into a little more, though, is the idea that there's actually this back reaction in that the planet actually can have an influence on the binary's orbit as well. The gravity of the planet is small, but not zero, and this can slightly perturb the binary's orbit, and in doing so, induce eclipse timing variations, or ETVs. Historically, we have used ETVs to constrain or measure the masses in the known transiting planets, since ETV is a function of the planet's mass. So for Kepler-16, for example, we have ETVs on the order of a couple of minutes, and we can see the signal to noise is not great, but it is measurable. And so this is how we know Kepler-16 has a mass of about a third the mass of Jupiter, and that can be known without there being any radial velocity follow-up. On the other hand, for most of the systems, you have something like this for Kepler-413, where the ETVs are consistent with zero, so you can only provide an upper limit on the planet's mass. And whilst this is not as good, it's still important because this upper limit shows it is indeed a planet. It's not just a eclipsing third star. It is indeed a transiting circumbinary planet. What I'm interested in, though, is using ETVs to discover brand new planets, planets that actually are not transiting, because this would allow us to avoid this bias of having the planets aligned with the binary. Now, there was some cool work that popped up a few years ago, led by Gepley and a bunch of guys down in Australia, and they found this particular system, KIC 50 blah, 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 with ETVs, again, on the order of a few minutes. And the signal to noise was so high and beautiful that they were able to deduce that this was a very large circumbinary planet. 7, 8 Jupiter masses, way bigger than anything we'd ever seen. And this is purely from ETVs. No radial velocities, no transits. Now, this was very exciting because not only did they find the most massive planet known so far, but they also proposed this really wacky orbit. It would be sort of like a polar orbit. The binary's going around this way, and then the planet's going around something like this. It's about 110 degrees misaligned. And this was exciting because I'd been excited about finding misaligned planets for a long time. This is, again, sort of probing planet formation at the extreme. We know there can be misaligned circumbinary disks. We know that planet-planet scattering or planet-binary scattering can induce misalignments in planets. So it would be great to find a misaligned circumbinary planet. However, we thought it would be worth digging a bit deeper into the existing data and also getting some new data to really try and confirm this system. So this is work led by Max Goldberg, starting back when he was at UChicago as an undergrad. Now he's at Caltech as a grad student. What we can see is that if you purely look at the eclipse timing variation, then it is possible that this is a wacky misaligned system. What we are looking at here is the argument of the ascending node versus the inclinations. The inclination is essentially the distance from the origin. So a point right at the origin means coplanar, then you got a little ring at 90 degrees, and then the outer ring is 180 degrees, i.e. something that's aligned but completely flipped. And we see that most of the solutions, i.e. the colored solutions, which are good solutions, kind of around the middle, which would correspond to a nice coplanar simple orbit as we would expect. But there are a couple of these little bubbles at these more highly misaligned solutions like what Getley found. Now, this looked interesting, but the eclipse timing variations don't say everything. What you also need to account for is the eclipse depth variations. And what we see in the data, as shown on the left, is that if you phase fold every single eclipse in the data over 4 years of Kepler, the eclipse shape, depth, width, duration, none of it changes. Whereas on the other hand, the solution proposed by Getley would have a significant change in the eclipse depth over time. Basically, this massive planet is tugging on the binary's orbit and changing its alignment slowly over time. So therefore, whilst the timing says it's possible, the depth variations, or should I say lack thereof, do not allow for it. So we provide a solution where it's actually coplanar. So to summarize, we are able to confirm this system is indeed a real circumbinary planet. It is the first circumbinary planet discovered with eclipse timing variations, and of course the discovery was led by these previous authors. And it is indeed very big. We get a mass that's a little bit lower than theirs, but I mean, whatever, it's close enough. It's a big boy. But it is coplanar. So whilst this method does open the opportunity to finding lots of misaligned planets, and I'm really excited to continue to try and apply it to more systems, this particular one is coplanar. But now we get on to, let's go back to the OG method for finding exoplanets, radial velocity spectroscopy. BBOP is the radial velocity survey that I started with Amory Trio when we were back at Geneva back in 2014-ish. Binaries escorted by orbiting planets. It's one of the better acronyms I've ever come up with. I think it's the only acronym I've ever come up with as well, though. There are a couple of challenges that we have to get around. There's a reason why RVs are the original method for exoplanets, but have never found a circumbinary planet. One is that you've got this huge radial velocity Keplerian amplitude just from one star onto the other. And the planetary signal, which we'd want to see in the residuals, is buried deep beneath that. We're talking many orders of magnitude smaller effect. So that's one problem. And the other problem is that you've got not just one set of spectral lines, but you have two, and they're convolved with each other, and they move back and forth. And whilst finding radial velocities of double-lined spectroscopic binaries has been done for a while, to do it to a precision to see a planet in the residuals is a unique challenge. So with BBOP, we've received, I dare say, some very generous time allocations. We started off with the Swiss telescope, Geneva, then we literally upgraded by going up the hill to HARPS, where you just get a much better precision and long-term stability. We also expanded to the north, where we got a similar amount of time on Sophie in the beautiful French countryside. And then also a couple of nights here and there on Espresso, just to see what would be the absolute limits of our precision. And so I'm going to present you two preliminary results from BBOP, which I'm pretty excited about. One is going to be the first ever circumbinary planet radial velocity detection. I'm sort of emphasizing that word detection, because the system is Kepler-16. Kepler-16, the original first circumbinary planet. We can see here radial velocity orbit of the binary, kilometers per second amplitude, absolutely huge. But then in the residuals, the periodogram shows the residuals have a spike at about 230 days, which corresponds to that transiting planet. So with BBOP, we're able to detect Kepler-16 purely in radial velocities. This fit does not include the transit photometry at all, although of course we are able to compare. One thing that's nice is that rarely do you ever get to compare the mass from radial velocities, the sort of gold standard method, with the mass that comes from the ETVs. But it's really nice here that we see that they match very well. But of course, this is a radial velocity detection. We didn't discover Kepler-16. It was already known. This was really a proof of concept. Our first discovery comes in this other system. This is EBLM J0608, and this guy has an interesting history. We were following this from about 2013. It was one of our original sample targets, following it purely with radial velocities. Then TESS comes along, and TESS finds transits. And so this system has a 14-day binary, which in radial velocities corresponds to this big peak in red. It also has a 90-day transiting planet, which is pointed out here as PB. And curiously, that is not seen in the radial velocities. What we do see, though, is PC, i.e. the radial velocity signal of an external planet. So it's a brand new planet found purely with radial velocities, but in a system which has another transiting planet. And so we can see that even though the individual data points maybe don't look amazing, as is often the case with RVs, you need to stack a bunch together, and we can see a quite clear Keplerian sinusoid coming out. Radial velocities are nice because they can find longer period planets. They can also potentially find misaligned planets. We don't actually know what the misalignment of this planet is, but we're not required for it to be edge-on. And so whilst this is only our first discovery, I would like to hope that it's the first of many. And so indeed, I think this is why. As we move forward, we want to focus not just on the transiting systems, but indeed these non-transiting circumbinary planets. I say thank you very much for your attention. Thank you for accommodating Australian time zone differences of 14 hours. I'm rather sleepy, but I'm also jacked up on coffee, and I'll take any questions.
All right, thank you, David. We have time for a couple of quick questions. Are there any in the room first? I don't see any hands. Are there any online questions in the chat? Okay, well, I guess your presentation was so great that nobody is confused on anything.
Everyone's as jacked up on coffee as I am. Thank you very much.
I do have a quick question. How do you anticipate this ETV and method being used with future telescopes? I mean, you talked about Bebop, which I take to be a ground-based effort, but what about, we've got a lot of facilities in space and on the ground coming up that we're excited about, including the Webb telescope and Hubble and so forth. So do you see ETV being something that's used with ground-based, space-based? What do you see for future facilities using these methods?
I think what's really cool with the ETV method is anything that can give you, essentially improve your lever arm with the observations, i.e. baseline is good. So we're going to struggle to match the individual measurement precisions of Kepler. Like TESS can't match Kepler's individual measurement precisions. And it's very hard to get time on the other telescopes you mentioned. But what TESS can do is TESS can take a small amount of lower quality measurements, but a long way apart in the future. And that means that they are still quite informative. And beyond that, ground-based is reasonable because these are really deep signals, so it's quite easy to see from the ground.
Okay, let's thank David again.
Thank you.
I think that should be shared now. Yes, you can use that one.
Okay.
Okay, so our next speaker is going to be Gudmundur Stephenson from Princeton University, who's going to be talking about the warm Neptune GJ3470 and its polar orbit.
Thank you, Megan. Just wanted to test if people online can hear the mic. guess I'm gonna take that as a, okay, there are some thumbs up, great. So I guess with this mic, can I then move around? I guess I'll take a second. So yeah, there is a red light over here. Okay, now it's green. Okay, now I can hear it. Okay, awesome. So yeah, I'm really happy to be here. My name is Gudmundur Stefánsson, and I'll be starting my second fellowship at Princeton in a couple of months. And today I'm excited to talk to you about this really exciting system called GJ3470b, which we've demonstrated for the first time has a polar orbit. And GJ3470 joins in a growing group of these warm Neptunes that are observed to be on polar orbits and have evaporating atmospheres. So let's dive right in. So one of the big surprises in exoplanet science is the realization that many exoplanetary systems are not on sort of well-aligned orbits. This goes back to what David was just talking about. They're not necessarily these flat pancake systems, but they can often be seen on these highly misaligned orbits. So the solar system is a flat pancake system, something similar to what I'm showing here on the left. And in this context, it's useful to define a quantity called the obliquity, which is then the angle between the stellar rotation axis and the planet orbital axis. And for well-aligned systems, the obliquity is close to 0 degrees. However, observations made over the last decade or so have shown that many exoplanetary systems are on highly misaligned orbits. And something similar to what I'm showing there on the right, where psi is then much larger than 0. And measurements of obliquities are then a key tool to allow us to gain insight into how planets form and evolve, because if we do see that an exoplanetary system is highly misaligned, the question immediately arises, oh, how did that actually occur? Were there some gravitational interactions, planet-planet scattering, like David was talking about, that kicked maybe the planet into a highly misaligned orbit? So how do we make obliquity measurements? There are a few different ways. David talked about one really cool way with these eclipse timing variations. And another way is with the so-called Rossler-McLaughlin effect, which is an efficient way to make obliquity measurements. Here I'm showing how the RM effect actually works, which then relies on measuring the apparent radial velocity anomaly that occurs during a planetary transit, when then a transiting planet crosses in front of a rotating stellar disk. Here I'm then showing a star rotating around its rotation axis, causing one hemisphere to be blue shifted and the other to be red shifted. And as a planet crosses in front of the rotating stellar disk, it successively blocks out differently blue and red shifted parts of the stellar disk, causing an apparent radial velocity anomaly that we see by taking precise radial velocity observations during the transit. And the shape of this curve is highly reliant to the sky projection of the obliquity, lambda, over there. And the amplitude is related to the size of the planet and the rotational velocity of the star. However, there's a problem with the RM effect that it's only sensitive to the sky projection of the obliquity rather than the true 3D obliquity angle, which is what the planetary dynamics are actually reliant on rather than the arbitrary sky projection. However, fortunately, if we do have a measurement of the sky projected obliquity, together with two additional angles that I'm showing over there, we can constrain the true obliquity angle psi. For that, we need to know those two additional angles. IO over here, which is then the inclination of the orbit, which fortunately is well constrained for transiting planets, usually around 90 degrees. And then we also need to know the inclination of the star, I over there. There are a few different ways to constrain stellar inclinations. One of those ways is to use an equation something like this, where we leverage information about the rotation period of the star, for example, from outer transitometry, the spectral broadening of the star, of the VSNI, and then the size of the star. So what does current then obliquity measurements actually look like to date? Here I'm showing then sky projected obliquity measurements as collected together in a really interesting paper led by Simon Albrecht et al. Just published last year, which shows then sky projected obliquities as a function of stellar effective temperature, demonstrating a broad distribution of obliquities from 0 to 180 degrees of sky projected obliquity. You can ignore the color code for this discussion. But in this very interesting paper, Simon Albrecht and others went through and actually systematically calculated true obliquities whenever they could. And in so doing, they found something very interesting. So what did they find? when calculating true obliquities, this brings into focus a bifurcation in the true obliquity distribution of this planetary sample, where this sample of planets is preferentially seen to be on well-aligned orbits, something similar to this, or close to polar orbits, with few planets in between. So this is very interesting because on the theoretical side, what causes this? Why don't we see planets that are with obliquities somewhere in between, even in retrograde orbits? And this raises a number of different theoretical questions. And then also on the observational end, is this dichotomy also seen for smaller planets? Because this sample of planets is completely dominated by hot Jupiter systems, these really large planets orbiting really close to their host stars, just from the virtue that those are the most easiest to measure. But hot Jupiters are a relatively infrequent outcome in planet formation. And so it's not clear if this is then probing then a property of the hot Jupiter population, or if this is more generally seen for more smaller planets that are much more frequently seen. So I'm really interested in now to use next-generation radial velocity spectrographs to gain further insight into measuring obliquities of small planets. And I've been using one such spectrograph called NUID, which I'm on the instrument and science team of, which I'm showing over here. This is a next-generation radial velocity spectrograph that we just finished installing and commissioning on the WIN 3.5-meter telescope at Kitt Peak in Arizona. Here I'm showing an exploded view of NUID and of the WIN telescope on the right. NUID has a high resolution of around 100,000 and covers a very broad wavelength range from 380 to 930 nanometers, making it an excellent radial velocity machine across a broad array of stars, FGK, and even M stars. And really the goal that we set out to tackle when building and designing NUID was to really push the boundaries of what has been done in precision radial velocity observations. And as part of early science and commissioning, then we wanted to sort of push NUID to its limits. And one of the targets that I was interested in measuring, we're doing an arm effect observation of, is this system called GJ3470b, which is a really exciting warm Neptune that we had studied previously with another spectrograph called HPF on the 10-meter Hubble-Eberly telescope. So GJ3470b is a warm Neptune. It has a period of around 3.3 days, and it's on a mildly eccentric orbit. So there is some indication that there might be something dynamically interesting there, because there is then a mild eccentricity that we see. And in previous work that we have done to study this system, we've demonstrated that it shows signatures of helium-1030 absorption. I won't be able to go into the details of those observations in this talk, but that, the long story short is that that is a telltale signature of an evaporating atmosphere. So there's definitely something interesting going on in this system. It has a mild eccentricity and an evaporating atmosphere. But the obliquity, which is another probe of planetary dynamics, had never been constrained before. And we then used NUID to observe the arm effect of GJ3470b in two different transits that I'm showing over here. The first one was of higher signal noise due to better seeing conditions that night. And I'll walk you through the data over here. Here I'm showing the radial velocities as a function of time. And the data go during the transit down and then slowly go up back to the baseline. So this is a telltale signature of a misaligned planet, where the expected well-aligned case here is shown with a gray dashed line, which we are ruling out to a high degree of confidence. And indeed, the data are fully consistent with a polar orbit obliquity around 90 degrees. So where does GJ3470b land with respect to obliquity measurements of other warm Neptunes? Here I'm showing true obliquity measurements as a function of stellar effective temperature, highlighting here in particular Neptunes on circular orbits in blue and on eccentric orbits in red. Other systems are shown in gray. And I don't know about you, but I think I'm seeing the same bifurcation here for the warm Neptunes as well. But additional observations are certainly useful to continue to probe that. And some of the systems that I'm really interested in is this group of planets, which share some very common characteristics and properties. So GJ3470 then joins this group of warm Neptunes. They're all polar. They're all eccentric or mildly eccentric. And if we look at their atmospheres, they all have evaporating atmospheres. So this raises questions of, oh, is there maybe some connection between how these planets formed? Maybe they formed further out. Maybe there's an outer companion in the system. They interacted gravitationally, kicking the inner planet into a highly eccentric orbit, causing it to come to close encounters with its host star, which tidally dissipates some of the energy, causing the planet to migrate further in. And in so doing, with the increased then intensity of solar radiation from the host star, causes the atmosphere to start to evaporate. Interestingly, two of these systems, those over here, HAT11 and WASP-107, have known outer companions, but GJ 3.70b did not have a known outer companion. We obtained additional ground-based radio velocities with HPF, and then compared that to literature radio velocities spanning 12, 14 years or so, where we detect sort of a slope sort of at the 2 sigma level. Not decisive, but suggestive of a candidate slope. And additional radio velocities, along with Gaia astrometry, will be particularly helpful to constrain that possibility of an outer companion further. But in a paper that we just published earlier this year, we show that if we assume that this is due to an outer companion, it would be able to explain the eccentric and polar orbit of GJ 3.70b. So I'm excited to continue studying that system and other systems like it. I've been leading some other observations with NUID and other spectrographs, Maroon-X, and there are other really exciting spectrographs coming online, like the KPF spectrograph, which will be really exciting to use for ARM effect measurements like this. Here I'm showing a collage of a few ARM observations that we're currently working on publishing, that we haven't published yet, just to give you a sneak peek. We have 4 additional warm Neptunes measured. 3 of them seem to be fully consistent with well-aligned, and then 1 of them could be polar, the one on the right bottom over there. And I've also had the fortune to work with a talented undergraduate that is leading the charge, Robert Frazier, who will be applying for graduate schools in the fall, and he's leading the charge on one of those systems, so stay tuned for his paper coming out soon, along with the different papers on the other systems. And with that, I'll conclude. I'll be happy to take any questions.
Right, looks like we have a couple questions in here. If you could pass that back.
Hi, Gumi. So if this dichotomy is real, can you say a few of the implications for planet formation, some of the ideas?
Yeah, there is one mechanism that I didn't get a chance to go into, that sort of has, what is really interesting is sort of what actually tends to cause the planets to sort of stop at 90 degrees. Why don't they go further, even to retrograde orbits, something like that? So there is one mechanism proposed by Petrovich et al. That we considered in our paper from earlier this year, that sort of has a preferential stop at sort of the 90 degrees. It tends to tilt the orbits to preferentially 90 degrees, whereas there's sort of a equilibrium there. And that has to do with the ingredients that go into that mechanism are sort of an outer companion, along with interactions and resonances that occur during the disk dispersal phase, that causes the inner planet to sort of get tilted to 90 degrees. I'm not an expert on the theoretical side of those things, but that is one very promising mechanism that we want to put to the test on some of these systems. There's also another one, lead of Kozai, which can also, in some circumstances, depending on exactly how inclined an outer companion would also be able to explain highly eccentric and highly misaligned orbits.
So I have a question. I'm not sure you kind of touched on it, I think, but would it be possible in these kind of scenarios to have like an aligned set of planets and then one that's misaligned in the same system?
Yeah, so there has been, then there are some systems of ultra short period planets where I guess there is sort of a pancake system, and then the innermost planet is tilted. Ferry, who is here, he is an expert in those types of systems. There is also another one that has been claimed to have a inner one that is highly misaligned, and then an outer one that is fairly close to well aligned. And certainly, some of these have outer companions, so for example, if the GJ3470 slope is truly due to an outer companion, then most probably we would expect it to be not at the same inclination, although we don't exactly know. But yeah, great question. Mm-hmm.
One of the puzzling things about GJ3470b is the low metallicity that has been inferred with the spectroscopic observations.
Mm-hmm.
So I was wondering if one of the models that you were showing could explain that. I was just thinking that if there was some migration through the disk, that would have increased the metallicity. But if it's just like moving in a place where it's not interacting with the disk, maybe that could be giving it the low metallicity. I was wondering if the two models that you showed have any implications to the observable atmosphere.
That's a great question. That's one area that I haven't thought about on sort of the metallicity of the star and of the planet. So certainly one area that would be interesting to probe further. But yeah, I'm not exactly sure, like within the two sort of models that we consider there, what the implications, I guess, would be on the metallicity of the planet. But that's a great idea.
All right, for the sake of time, we're going to have to move on, but let's thank Gilminder again.
Thank you.
All right. So our next speaker is going to be online again. Stop sharing. There we go. Yeah, so Kevin, you should be able to share your screen now. Our next speaker is going to be Kevin Wagner from University of Arizona.
Great. Hi, everyone. Somebody please stop me if you can't hear me. So thanks for the opportunity to share some of what I've been working on recently. Today I'd like to talk to you about mid-infrared imaging of habitable zone exoplanets. And I won't actually be talking too much about planet formation. And I think the reason why I got lumped in with the planet formation talks is because traditionally the field of exoplanet imaging has really only been sensitive to these warm, young, giant planets. And it gives us a handle on studying planet formation. But we want to move away from that. We want to move toward these colder, more mature, and smaller exoplanets. I'm going to tell you a bit about how we plan to do that. So for a little bit more background, as I said, most exoplanet imaging efforts have focused on young giant exoplanets that still retain a significant amount of heat from their formation. These planets radiate most of their thermal emission in the near IR, or at wavelengths of about 1 to 2 microns. And if we want to image thermal emission from cooler and more temperate planets, including habitable zone planets around mature sun-like stars, then we need to go to longer wavelengths, or to wavelengths of about 10 microns, where these planets radiate most brightly. We also currently need to do this from the ground, since JWST lacks the inner working angle capabilities to compete with extreme AO systems on large ground-based telescopes. So in order to image thermal emission from these colder planets, the techniques of exoplanet imaging that have primarily been used in the near-infrared, like adaptive optics and coronagraphy, will need to be extended to the mid-infrared. The primary limitation here, which might be obvious, is that the Earth's atmosphere, the telescope, and the detector are all also glowing brightly at these wavelengths. And of course, going to longer wavelengths also means dealing with a larger PSF. Here's an example illustrating these challenges. These images show the HR8799 system imaged at 4 microns and at 5 microns with the NERC2 instrument on Keck. These observations were taken with the same instrument under similar conditions and for approximately equal. The difference in the images you can see. Are you hearing an echo?
Yes. If there's somebody who's unmuted who's not Kevin, could you please mute?
I think it may be these.
It might be those.
Okay, let me try again. So yeah, these observations were taken with the same instrument under similar conditions and for approximately equal amounts of time. So the main difference here is really the wavelength that we're observing at. And the difference can be seen both as a higher thermal background that's present everywhere throughout the image, and also as a more extended interspeckle pattern, since the diffraction pattern also scales with wavelength. And planet E is even lost among the speckles in the 5 micron image on the right, and you can imagine that these issues are even more pronounced at longer wavelengths. But let me take a step back for a moment, because I also had a video of this same planetary system imaged at 2 microns here, and you can really just see how much better the detections of all of the planets are when you go to shorter wavelengths. And that's because these planets radiate primarily at these shorter wavelengths, and also because we're just dealing with way less noise also in the observation. Okay, so despite these challenges, let's take a moment to consider what might be possible if we could achieve a similar level of performance at 10 microns as we currently can in the near-infrared, which is a contrast ratio of about 10 to the minus 6 or so at a separation of about an arcsecond. Or for very bright stars, maybe a bit less than that, like 10 to the minus 7. So the plot on the left shows the contrast ratios of hypothetical Earth analog planets around nearby stars. And these planets are Earth analogs in the sense that they have an Earth radii, an Earth-like atmosphere, and receive an equal amount of radiation. And among this sample, these hypothetical Earths around two stars, our nearest neighbors Alpha Centauri A and B, lie within the range of sensitivity that has currently been achieved with extreme AO systems, and now even more than about half a decade ago. And the habitable zones of these stars, like Alpha Cent A and B, Sirius, and a few others, notably are at separations of about an arcsecond, which can be resolved with current telescopes in the mid-infrared. And beyond large aperture telescopes, there are a few key pieces of equipment that make exoplanet imaging possible in the mid-infrared. The first that I want to tell you about is an adaptive or deformable secondary mirror. And in my opinion, this is a pretty remarkable piece of technology. The glass shell that you see sitting on a bed of neodymium rare earth magnets that hold the mirror in place and also act as magnetic actuators to control the mirror's shape. This enables us to perform an adaptive optics correction at the secondary stage, still running at a pretty fast rate of about 1 to 2 kilohertz, and to eliminate additional warm optical elements that would otherwise contribute to the overall thermal background. Another important piece of hardware is a mid-infrared optimized coronagraph, or in this case, an annular groove phase mask, or AGPM. This sub-wavelength grating acts like a pair of polarized sunglasses, except the polarization vector performs a complete 360-degree turn around the center of the mask. This creates an effective central null, which occults the light from the star while allowing off-axis light from planets and other objects to pass through. These AGPMs have been used pretty widely in the near-infrared, and transitioning to longer wavelengths is pretty straightforward since the etching pattern also scales with wavelength. And the final important component that I want to tell you about is the observing strategy for mid-IR exoplanet imaging. In order to enable measuring and subtracting the relatively high background from the images, and a lot of this is coming from the detector, we need to perform rapid chopping at about 10 hertz, or pretty close to the frame rate, in which we alternate the position of the star on and off of the coronagraph, or really, if we weren't using a coronagraph, just altering the position of the star anywhere on the detector. And then by subtracting one image from the other, most of the systematic features, in particular the excess low frequency noise from the detector, cancels out, resulting in essentially background limited performance, which enables planets of very low masses to be detectable with sufficiently long exposures. And this strategy will be important to keep in mind for later. This slide shows the final combined image from the NEAR campaign, which was the first long-stare mid-infrared observation of Alpha Centauri, in which we used the VLT to observe Alpha Cent A and B for about 100 hours. These images each include a simulated warm or cold Saturn-sized planet or warm sub-Neptune-sized planet in order to give you an idea of what a true source would look like in the data, and also to enable us to characterize the sensitivity. So in terms of radii, we're only about a factor of 2 away from being able to detect a warm, rocky planet, or something on the upper range of super-Earth radii. Or in other words, we're about a factor of 4 away in terms of sensitivity, and that's a gap that we're pretty confident that we can overcome with continued progress. I should mention there is one plausible planet candidate in the images, labeled as C1, but ultimately the nature of this will require further verification. We're relatively confident that this isn't a random false positive because it appears in multiple independent segments of the data, but we can't presently rule out an astrophysical false positive like a zodiacal disk, or an instrumental false positive for some that could be a result of some of these. So building on the work of NEAR, as a SAGN fellow, I've been leading a large program on the LBT that's focused on implementing many of these lessons and also on developing some new strategies in order to perform mid-IR exoplanet imaging with the currently only existing ELT prototype. This program is called LESSONS, which stands for the LBT Exploratory Survey for Super-Earths and Sub-Neptunes orbiting nearby stars. And as of this past summer, we've completed all of our planned upgrades. And I'm excited to see what we can do on sky as we head back into winter, which is the best time for our observations due to the lower thermal background. I'm also excited to tell you that even before achieving full sensitivity, we've detected our first candidate. This is likely a brown dwarf orbiting at about 2 AU from a nearby star. The mass is quite uncertain because what we're really measuring here is a combination of radius and temperature. What I find makes this candidate compelling is that it's detected in at least 4 epochs. From a single night to a single night, it stays in the same place, and over about a month, you see about this 20 degrees, or 20 or 30 degrees of what's consistent with orbital motion. So we're planning to follow these observations up in a few months, and hopefully I'll have more to say about this and also other candidates in the near future. For now, we're still using the chopping strategy with LBTI, and by ramping the chopping frequency up by more than a factor of 5, we've noticed an exponential decrease in noise, which is similar to what we found with NEAR. We're still not chopping quite as fast as we were able to with NEAR because we're running into the electronic limits of our the limits of our detector's electronics. And again, this method allows us to remove the dominant source of noise and to integrate longer and to continue to build up a signal-to-noise ratio. But ultimately, the most exciting capability that we plan to implement with the LBTI is Fizeau imaging. In this mode, we overlap the PSFs from the two telescopes coherently on the detector to enable imaging with the resolution corresponding to the 23-meter baseline of the two telescopes. This enables the LBT to be used as a prototype ELT and results in about 3 times higher spatial resolution and also sensitivity compared to observing with a single 8-meter telescope alone. However, this mode requires us to observe, requires stable observations for upwards of a few minutes so that we can keep our phase loop closed, and therefore it's completely incompatible with our chopping strategy. And in that case, we just get completely overwhelmed by the systematic noise. So to implement Fizeau, we're going to need a new detector, and we're working on securing funding for this upgrade. And finally, I just want to leave you with one important scaling relationship to think about. And that's that the time that's required to reach a particular signal-to-noise ratio scales as the -4th power of the diameter of the primary mirror. That means that the upcoming ELTs will be able to complete in just minutes what currently takes us hours, or equivalently, what would currently be completed in about a month-long observing campaign to image a super-Earth around a nearby star will soon be able to be completed in a single night. So in summary, with NEAR, we demonstrated that it's possible to image nearby habitable zone exoplanets in the mid-infrared, and as we observe for longer, we continue to gain sensitivity. In about 100 hours, we're currently about 4 times away in terms of sensitivity from detecting a possibly rocky planet. We're continuing to build upon these methods with LBTI. In the lessons survey, we have our first candidate that we're excited to follow up. And in the next decade, the ELTs will be able to efficiently utilize these methods to image nearby rocky planets around a greater number, but still speaking about just a handful of nearby stars. But I think these are probably some of the more exciting planets since they are so close and we could potentially learn a lot about them. So thanks again for your attention, and I'd be happy to take questions.
Maybe this time we can start if there's any questions online. No? Okay. Any questions in the room then? Yeah.
Hi, Kevin. Great, cool results. I was wondering about the NEAR observations. They were taken over quite a long time period for an object on a relatively short orbit. So do you need to take into account the orbital dynamics when you stack the data to detect?
Yeah, so thanks for bringing that up. That's actually an interesting kind of side discussion here. So in these images, what I've done is just simply stacking the images on top of each other. So it was taken over about a month. The planet on a 1AU orbit would move by about, a little less than a month, 2 weeks or so. So we would expect about 10 degrees of orbital motion over the course of these observations, which corresponds to just about 1 PSF width. So we actually do see a bit of elongation in the source when we co-add the data this way, and I think that might actually be a bit of further evidence that what we're looking at here actually is orbiting. And some of my colleagues have also utilized the K-stacker method to reanalyze these data, and actually the significance of this source improves if you do take orbital motion into account. I wouldn't say that that's saying definitively that we're looking at an orbiting object, but it certainly looks positive.
Thanks.
Hi, Kevin. Thank you for your talk. I'm aware that LBT has a fancy way of splitting the light. I was wondering if we can do anything to take the spectrum of these planets, and if we can take the spectrum, what wavelengths would that be at?
Yeah, so for this candidate, which actually is quite a bit brighter than the NEAR candidate, we can see this one on single nights. That might be something that we could think about in the future. We're still getting a signal-to-noise ratio of just about a few in a single night in the broadband filter. But maybe once we have Fizeau up and running, some of these kind of easier targets we will be able to also get a spectrum of.
Thank you.
All right, any other questions? Oh, yep, one more.
Hi, thanks for the great talk. I was wondering if you could talk a bit about what limits this method in space. If the mid-infrared foreground effectively disappears in space, and why? What is there scope for doing anything similar?
Yes, absolutely. So unfortunately, James Webb is really running up right into the limitations with its inner working angle. For alpha Cen A and B, we can probably push down to maybe a few times in Earth radius, conservatively maybe 4 or 5 Earth radii in the habitable zone of alpha Cen, probably closer to the outer zone of the habitable zone of alpha Cen. That's really where the limitation is coming from, is with the amount of wavefront air in the telescope, which fortunately is better than expected. So hopefully we'll be able to follow up the near candidate and maybe also discover a few more with JWST. But really, I think that what's going to push this forward is large aperture telescopes on the ground, and coming up with ways to reduce the thermal background, and in particular, the background that's coming from the instrument itself.
All right, let's thank Kevin and all the speakers in this session again.
Thanks, everyone.
So unless the leads have any announcements, yeah.
It's a fast first session, so it's time for the coffee break. I believe it's set up in the cafeteria, though there may be some stuff out front too. And come back here in was on? Now it's back on. Right.
Everyone back at noon.
Everybody come back at noon, please. Enjoy your coffee.
Clap for
Wherever
you
when
it's
whether
time.
you get it here or somewhere else. Go ahead and enjoy it.
Ooh, that is not good. You're supposed to just do that for effect, not for...
And you said something really cool. Yeah, I saw that you said.
Yes. Yes. Well, we can talk to, yeah, why don't you go talk to Valory, make sure it's all, I think they'll ask him for ID.
Okay. And maybe I could I'll set up a meeting.
Well, I don't know if they'll let you do it or they'll need me or what, or Flory, but I think basically they've got his name. I think that'll be enough. But so this is the pointer, but I never was able to get it to work. And Thomas was supposed to do so. Thomas. Here it is. Here it is. See, look. Dawn. Okay. The pointer. It's just not very visible on it. Con, see, you just hold this button. Yeah, and then you just move.
Okay, I thought you did that, but it didn't work. Okay, my bad.
No, it's very touchy. I tried this. No way. I know. So I yeah. And it, what?
Our first speaker.
Remote. I don't know. Yeah. So.
Look on the schedule. On the schedule, she's on the schedule. Have a little. Not completely.
What is it? There we go. You're tomorrow.
Oh, okay.
You're group 3. That's tomorrow. Oh no, yeah, you're the first person in group 3.
Okay.
So your tomorrow looks like.
Oh, that's and it's at 1. Okay.
Is that a problem?
No, I'm leaving it too.
Wait, so what time? Yep. What time is group 2?
Group 2 is at 1:45.
Okay, there's no time.
Well,
A time on it. For when group 1 goes, when group 2 goes.
We just go to the first that's at 1 o'clock.
Yeah. Okay.
And the
But
second
so what
group?
about the second group?
but so he's going to come down here and pick them up.
Yes. I didn't know the exact time, so I didn't put it up.
It's 1 o'clock. At 1 o'clock and 1:45. What?
So what time does group?
1:45.
Okay, so can we?
And that's a I can.
Well, yours I could not. I had to do in numbers because yours didn't show the groups numbers. What your had when I put it up, it didn't show group 1 and group 2. So I did it in. But I think we could just tell people, even odd number groups are at 1 o'clock, even number groups are at 1:45.
Yeah, that's easy. But if you want to get updated.
No. I think we could just tell people. I think they're pretty sharp.
Yeah. So chair, yeah, we should get session chairs to sit up here. Yeah, they can waive these things.
Okay, I don't know, but our thing with her because she can't.
Sarah Pearson?
So, yeah.
You said
She's not.
Oh,
well, I just said there's cancellation for the symposium. Yeah, so she's getting married this weekend.
Oh, right.
I guess.
If this is still a public dinner, yeah.
So, yeah. So I guess we're all. That's not hard to see.
I think you already talked about your study. I can go and tell. Yeah, well, we haven't put the schedules properly. Watching on YouTube and so on. This is all
So everybody should be yeah. So if she's not here, these 3 people transitions going through here, we will be.
I'm still not bringing up the next slide.
I was just hoping. Yes. Right. So I was able to talk in the next session, and her email was big, and she was.
Oh, you want to?
Yeah, let's try it.
Are you okay?
Yeah.
Yeah.
I mean, I guess also because of the online. So if you go scroll up, there's some movies.
Yeah.
Let's just play it.
Let Don start.
Yeah.
I mean, this is a Mac, so it should be.
It should all be fine. Okay, I didn't know once it went through. I didn't know if this computer was.
No. So it basically, it's sitting on the disk. It's sitting on the local disk here as like a box drive. You can do that with so it's.
Yeah. So we'll start.
Well, but maybe we bring people back in. We can talk about the tours.
Yeah.
Let's bring people back in. We can talk about the tours. We can say, our next speaker.
No, I'm at 12:30.
Just to remind you to put this off.
Okay. Yeah, I think. Well, let's see. I'll do it. Right. Okay, good. I just wasn't sure.
You're right. Yes, I will.
I which she this morning.
Okay, so she's
so
gone.
I think she's going to.
She wasn't there. No, she wasn't there. I remember
She
meeting
introduced
her. I remember meeting her from the site register.
Yeah.
Okay.
Yeah, so I think she is still.
So the other one, massive share.
Yeah, I mean, we had a few last minute.
Yeah, so I want to check if I can check my week. Thank you.
Okay, yeah, you're welcome. Yeah, I mean, it's hard with the hybrid. And half these people are who were coming in person. I've had this a lot.
Yes.
Yes, okay.
Okay.
All right, so 1 o'clock and 1:45.
Yeah, that massive work.
So everything's in.
Yes.
Okay. Okay, great. Hi, Marcel. I wanted to say hello. I'm Jennifer Wiseman. Nice to.
Very good. I sometimes participate in the polls.
Yes, I know. I just wanted to touch in person.
Yes.
Nice. We're all meeting everybody in person. Yeah, hello. Yeah, Don, nice to see you. I'm glad you made the trip. Yes, me too. I almost was in Chicago yesterday. Well, I don't know why it is. No. Are you having open slots? Is there an open slot tomorrow? If there's open slot tomorrow, then not today.
I appreciate it because what I did at this 6 at work before the work is and then 5% tourism.
Okay, I can't do it today. But you can't do it today. Okay, let's check your schedule first.
You want
Is this all, is it at lunchtime or anything?
Yeah.
Do you have any openings tomorrow? Let me see that.
Well, we can ask Paul to switch her and do it. Let's schedule for tomorrow. speaker on the program is actually
Oh.
the first talk. The first talk will be 12:15.
Okay.
But we have a little bit of information.
For folks who are online, the first talk of this session, Sarah Pearson, she was not able to make it, so the first talk will actually be at 12:15.
Got it. Thanks.
Well, the thought was that, you know,
Yeah, I'll talk about the doors. Hi, everyone. Welcome back. Yeah, our first speaker today is not going to be at the meeting, unfortunately. Yeah, and so we're going. But we're going to be recorded anyway. So, so yeah, our first speaker won't be here today. We'll be starting the actual talks at 12:15, right? So, but we have a couple of minutes, and so later today at 1 o'clock, we're going to start the tours of the MOC, the Mission Operations Center, and for JWST. And so we're only allowed to take 6 people in at a time. And so we've broken you up into groups. So actually the JWST did, and they did it in the imaginative way of alphabetical order. Sorry about you, Zabrowski, or yeah. So, my apologies. So, and yeah, it's, we really should have told them just do it reverse. Anyway, so if you're group 1, as it goes, the first tour is at 1 o'clock, and the second tour will be at 1:45. So that way, people who are going first will have a 15-minute tour or so, and they can come back and have time for lunch. Or the people starting at 1:45 can go and have lunch immediately, and then you'll have time to eat before you go on your tour at 1:45. So if you're an odd number group, you'll be 1 o'clock, and if you're an even number group, you'll be 1:45 each day. And yeah, and so Massimo Stiavelli, I believe, is going to be joining us here at 1 o'clock, and then Scott Friedman will be joining us on 1:45 generally in the order. We'll be finding all of you and getting him ready for him at 1:45 in the cafeteria. Yeah, let's see if we can see where you go. So, yeah, we should maybe mail this around. Oh, this is. Yeah, post it in this. We can post it in Slack. How do we do that? Yeah. Yeah. If you, I don't think that's a problem, is it?
I don't think so.
Wednesdays and Thursdays are more open.
If they need to know.
But you can also swap, right? You can. So we have a couple of, because we have a couple of spots open. I think I don't, but that could change.
Your slot, just email NHFP.
Okay, just the NHFP email.
Yeah, or just find someone you want to switch with, and just, yeah.
Thank you so much.
Yeah, and unfortunately, the restrictions on who you have to be a U.S. citizen or green card to go into the full mock, and so you'll get a good view of it, but you won't be able to go, put your fingerprints on the screens. So, but yeah. All right. Let's see. We almost time to start. Yeah, we're good to start. Yes. Yeah. Okay. But who is it?
Is that working? Hello? No? Huh?
Yeah, I know. But not working something? You should be. Can you hear? Yeah. Okay. Yeah. So our first chair today is Sultan Hassan.
Thank you very much.
We've never met in person.
Yeah, thank you very much. Okay, so for our first speaker for the session is Ryan Sanders. Good to see you. He's going to be talking about the gas metallicity relation over cosmic time. Please, while you're talking, just give me look at me here, because you have 1 minute, 2 minutes, 3 minutes, whatever, so I can warn you for the time, and you can take it away.
All right. Hello, everybody. Again, my name is. There we go. My name is Ryan Sanders. I'm a Hubble Fellow at UC Davis, and this is my third year in the program. So happy, at least on the third year, to make it for an in-person NHFP symposium here. And thanks to all the leads and everybody who has organized and run this program over the years, and then everybody organizing the conference this week. So today I'm going to talk about ways that we're working to improve the accuracy of gas phase metallicity measurements in galaxies across cosmic time. And metallicity measurements of the gas phase abundance in galaxies, in particular, often traced by the oxygen abundance, which is the most abundant of all metal species, as you can see on the y-axis of these plots, has been a major component in our understanding of galaxy formation and evolution. And in particular, the way that metallicity scales with galaxy properties such as stellar mass and star formation rate behaves in a very ordered way. We see a positive correlation between mass and metallicity, the mass-metallicity relation, but there's a secondary dependence at fixed mass where there's an anti-correlation on star formation rate. So at fixed mass, galaxies with higher star formation rates have lower metallicities. And these relationships have been interpreted in a number of ways over the years, but in particular, modern theories of galaxy formation have settled on how this tells us about the flow of gas into and out of galaxies. If you try to model these scaling relationships and you don't include things like the ability of galaxies to accrete gas and energetic feedback to drive outflows out of galaxies, then you simply cannot produce the metallicity trends that we see in galaxies. And these data are for Redshift 0 samples, basically from the Sloan Digital Sky Survey, where we've learned things about the strength of outflows and the relative efficiency of outflows at different masses, and how gas accretion is a large part of this picture as well. And so ultimately, establishing relations like these and then learning things about baryon cycling and galaxy formation is ultimately only as good as the measurements of metallicity that we have. And, this has been, over the years, a significant area of research is trying to establish the best ways to measure these metallicities, because it's not entirely simple. And ultimately, one thing that we can do with these scalar relations is compare them to results from large numerical simulations, such as Lustrous TNG here, and in particular, comparing to things like these metallicity scalar relations provides very stringent constraints on the baryonic physics that's put into these simulations. So things like the feedback parameters, gas and metal diffusion in the ISM, recycling of outflows being reaccreted back onto the galaxy. And so we'd like to be able to make very good comparisons here. And we'd also like to take measurements, robust measurements of these scaling relations to high redshifts, where galaxies were forming more rapidly. There's much more gas in galaxies. Cosmological accretion rates were higher. And we think that also the
feedback was more intense in these early galaxies. And so we'd like to establish what these metallicity scaling relations look like at high redshift and understand how things like gas inflows and outflows behave in the early universe. And to do that, we need robust ways of translating observations of galaxies spectroscopically into measures of gas phase metallicity. And we do this through tools called metallicity calibrations. I'm going to talk about some work that we've been doing on establishing the form of these calibrations at redshift 2 and some near future work that we're going to do with James Webb. So the way that we typically measure galaxy metallicities is using things called strong line metallicity calibrations. So you take measurements of what are bright emission lines in galaxies. They're very particularly easy to measure, so you can measure them in very large statistical samples. And you can use, on the right here, this plot is a translation between this particular line ratio, R23, and the metallicity, where the metallicity for a calibration sample has been measured in a more robust way using something called the direct method. So the direct method depends on measuring the electron temperature of the gas. If you have less metals in the gas, then the equilibrium temperature is higher. More metals, more cooling, lower equilibrium temperature. You can use the temperature to calculate the emissivities of the different lines and then infer the abundances in a very robust way. The difficulty with the TE-based direct method is that you need to measure these very weak, they're called auroral emission lines that are, about 100 times weaker than the bright lines like O3, 5007, and H alpha that we typically measure in galaxies. And so the reason we make these calibrations using small samples is so we can extend the ability to measure metallicity to very large statistical samples. But the key thing is that the properties of the large sample you're going to apply these calibrations to need to be similar to the properties of the calibration sample, or else the results you get out of this calibration will be biased. And because these auroral emission lines are so weak, we've basically only measured them for large samples at low redshifts. And so this is an area where we really need to improve to make the metallicities at high redshift more robust. So existing calibrations are based on redshift 0 samples. Do they work at high redshift? Well, if we thought the answer was yes, I probably wouldn't be giving a talk about it. We think the answer is no. We think there is some evolution in these calibrations. One particular piece of evidence is the excitation sequences of galaxies in line ratio diagrams, like the BPT diagram that you see on the left here. Basically, galaxies at redshift 0 in the gray distribution from SDSS, the star-forming galaxies trace a sequence in the BPT diagram from low metallicity, in the upper left down to high metallicity in the lower right. And it's a particularly narrow sequence that traces essentially the conditions of the ISM ionization in these galaxies. But if we observe higher redshift galaxies at redshift 1 and 2 and 3, we see that they actually get offset to different sequences in this BPT diagram. And the line ratio sequence is basically governed by the ionization conditions in the gas, properties like the ionization parameter, the shape of the ionizing spectrum, chemical abundance patterns, the density of the gas measured through the electron density. And to sum up what has passed several years of a lot of work on how these properties evolve in galaxies, we think that a number of these do evolve, and the result is that the metallicity calibrations must evolve as well. So we shouldn't go about cavalierly applying these redshift 0 metallicity calibrations to high redshift samples. So the easiest way, or I shouldn't say easy, the most straightforward way to address this problem is to actually measure calibration samples at high redshift by detecting these auroral lines in distant galaxies. And in 2020, I published a compilation of about 20 galaxies that had measurements of oxygen-3 auroral emission lines. And we started to get our first look at the evolution of metallicity calibrations. And with the sample, in particular, the sample mean that you can see in the black diamond here, if we compare this to redshift 0 calibration samples, such as this black curve, which is redshift 0 H2 regions, this magenta curve, which is typical redshift 0 galaxies in the Sloan Digital Sky Survey, we see marked offsets that represent the different ionization conditions in high redshift galaxies. But the sample is still small, and in particular, because it's selected off of oxygen-3, which is a high ionization emission line, we're really only measuring low metallicity, high ionization, and mostly low mass galaxies. And so we'd really like to be able to extend this to understand what's going on at higher metallicities that would overlap the parameter space where we think moderately massive galaxies live at these sort of cosmic doom redshifts of 1, 2, and 3. And to overcome this issue with the O3 based selection, one thing that we can do is actually to target a different set of auroral emission lines that are actually low ionization lines from oxygen 2, for example. And so that's something that we got some time on Keck Mossfire to do. We took some very deep Mossfire spectra of a number of bright galaxies in an attempt to detect these emission lines. These galaxies have very strong emission lines. They're fairly highly star-forming, but they're more massive, and so we think they're likely a bit more metal-rich than the galaxies that we measured direct method metallicities at high redshift before. And so the spectra I'm showing you here are from our ultra-deep Keck Mossfire campaign. This represents over 20 hours of spectroscopy, total integration across these 3 filters. And in particular, the highlight here, there's tons of lines detected. I mean, this is a super cool data set, and I've set here a preview of JWST metallicity studies because we think that measuring spectra like this is going to become much more common with JWST NearSpec. But the highlight is these little blips over here, all the way at the red end of the right-hand side of the spectrum where we detect these oxygen 2 auroral emission lines. This is the first time these lines have been detected basically above a redshift of about 0.2 or 0.3. So really pushing things to much higher redshifts here. And what we can do with this is then constrain the electron temperature and a number of different ionic and total abundances in these galaxies. And so if I go back to some of these metallicity calibration plots, we can add some new points on here. And in particular, one of these galaxies is much higher metallicity than the samples we've been able to measure here before. But it's ultimately still very challenging to do this with ground-based telescopes. And as you can see, the error bars are not particularly large here. The detections of individual lines are about 3 to 5 sigma in these targets. And so we still have a lot of work to do. So, you know, this sample is not good enough to use on its own merit to establish new metallicity calibrations. And it's really due to the limitations of working from the ground. So in the near infrared, taking spectroscopy from the ground, you have extremely bright sky emission background, many times brighter than your source, filled with also bright sky emission lines. And so if a weak emission line, like say 034363 is located anywhere close to a skyline, you're completely out of luck, regardless of how big your telescope is or how sensitive your spectrograph is. We also just have raw sensitivity issues. We're trying to measure very weak lines. And so even the most modern near-infrared spectrographs on 10-meter class telescopes, this is at the limit of what you can do with several hours of integration in a single band. We're getting marginal signal noise per source right now. And we're also stuck with fairly unrepresentative samples because we have to look at the brightest galaxies. And finally, we have the wavelength coverage issue. As I'm showing on the right here, just the atmospheric transmission in the near-infrared. We're limited to looking only in particular regions of the near-infrared wavelength range where we get high transmission. And if you take a look on the right here, this is basically a plot of redshift on the x-axis. And these colored bars show different redshift ranges where you get both the strong bright emission lines that we need to do things like dust correction and establish calibrations, but then also different auroral emission lines from which you can measure the electron temperature. And as you can see, regardless of which auroral lines you try to observe, there's very limited redshift ranges where you can observe this from the ground. So it's a huge challenge. And even if you have ELTs, 30 to 40 meter telescopes, they may have really sensitive spectrographs, but you're still limited to, you know, severely narrow redshift ranges to select targets. And so it limits your target density. And so what we're doing is moving to JWST. We have an approved Cycle 1 program called the Aurora Survey. That's going to take 64 hours of JWST NearSpec exposure across 3 different grading settings, getting uniform coverage from 1 to 5 micron for about 100 galaxies in 2 different fields. And we expect for about 50 or so of these galaxies will have significant detections of auroral emission lines. You can see a simulated spectrum on the bottom for a slightly above main sequence redshift 2.2 galaxy. So we're going to get very high fidelity spectra and be able to establish the form of these metallicity calibrations at high redshift. Also learn things about the abundance patterns of these galaxies, the ionization state of these galaxies. And so it's going to be a very exciting time. So unfortunately, you know, our program has not executed yet, so I can't show you data, but there's a lot of promise in NearSpec because it's already shown the ability to detect these auroral emission lines like 034363 for 3 gravitationally lensed galaxies at redshift of 7 to 8. And so the future is super bright here, and JWST NIRSpec is going to blow the door wide open on this science area. So I'm out of time. I'll go ahead and wrap up there. Thank you.
Thank you. Thank you very much for the nice talk. So questions in the room?
Hi, Ryan. Nice talk, Ariana Long. This is really exciting. You have abundance of really exciting optical and near IR data coming in. I guess I'm wondering if you've looked at all, or if there's plans to use ALMA to probe like gas, outflows, densities, and things like that, and compare what you're finding in the other part of the spectrum.
Yeah, so ALMA is actually really interesting for this science case. So one thing that's come out of ALMA, recent years is these dissections of far IR fine structure lines at very high redshifts, like oxygen 3, 88 micron. And you can actually use those in combination with hydrogen emission lines to do essentially also direct method abundances. And so there's another James Webb Cycle 1 program I'm leading that I didn't highlight here, but we're actually for 3 targets that have O388 micron measurements redshift 6 to 7, we're getting the rest optical James Webb spectra so that we can measure direct method abundances for those at these very high redshifts and do that. So yeah, that's a great thing. And also at redshift 0, trying to fold in the infrared data from like Herschel with local objects is also something that we're working on. So thanks.
Hey, this is really cool. So your program is going to give a sample, right, of 50 galaxies or so. Can you also use this NIRSpec data to say something about the methodicity calibration at redshift 7, 8?
Yeah, so it's difficult with just a few galaxies. To be completely honest, it's also difficult because the flux calibration of the NIRSpec pipeline is very unreliable at the moment. And the temperature dependence of the emissivities of these lines is highly nonlinear. So if you get the flux calibration wrong by 10%, then you could potentially get the metallicity wrong by a factor of 1.5 or 2. And so I think we really need to wait, A, for the pipeline to get better, which hopefully happens in the next several months, and then B, for larger statistical samples to build up. Yeah, it's also difficult for these 3 high redshift things to know if there's AGN contributing to the emission of these galaxies or not with the data we have right now. And that's something we don't want in our calibration samples.
So maybe one last question because of the time, maybe on Zoom. Do we have anything on Zoom? Any questions here? If not, let's thank Ryan.
Thanks.
Our next speaker is Thales. He's going to tell us about reionization survivors.
Hi everyone, my name is Thales. I'm at Princeton currently. Ultra high resolution simulations of dwarf galaxies. Just as a quick side, in case. Higher? Oh, now it's on. I made it go green, but. Sorry. Better? Yeah. Okay. Just as a quick aside, my name is Thales. I'm named after a Greek dude. But he was also an astronomer back in the day. He's known for his theorem, and I pronounce it the German way, Thales, so it's a little awkward. But just so you guys know, because I've been asked that before. So, why do we care about dwarf galaxies? So most of the small dwarf galaxies that we know are very local, either as satellites to the Milky Way or within the local group. But in the end, the study of dwarf galaxies is actually has to span, of course, all of cosmic history, and it opens up a whole bunch of questions also about their very, very early evolution. So everything from POP3 stars and the first star hosting halos and how large they were, given that most dwarf galaxies are known to have very ancient stellar populations. Also, because these are some of the least massive or least luminous objects in the universe, it really starts going in the halo mass or luminosity function regime where we don't know what it looks like at the low mass end. So where's the cutoff mass there? Other questions that we've been finding more and more ultra-faint dwarf galaxies, and how did they form? Where did they come from? And as I said, all of this goes to really kind of needing to understand the very early formation of galaxies themselves, and how they're affected by reionization, or how they affect and contribute to reionization. And then coming all together back to the local universe, how does this affect the total assembly history of even larger galaxies like our Milky Way? So, yeah, this is just a quick showing of most of the very small dwarf galaxies that we know are either, as I said, within the local group, or within at least the very close proximity to us. And there have been more and more detections as we get better with JWST. We're really expecting to find a lot more of these further away from us. And we just need dedicated models of galaxy formation to understand dwarf galaxies. And so I developed a model, it's called Lyra. And the reason for doing this, why should I not just be able to use other cosmological simulations, is that a lot of the choices for these other models were really made kind of with a focus on the Milky Way. And if you move away and say, I don't actually want to study the whole Milky Way, I want to study dwarf galaxies, then you get a whole range of new opportunities. So the mass of the Milky Way is around 10 to the 12. If you want to study all of the particles for a simulation. So you get like a factor, 3 orders of magnitude less particles in an average dwarf galaxy at same mass resolution. And for the radius or spatial resolution, it's the same. You go from a real radius of like 300 kpc to like 30 kpc per dimension. So you get another 3 orders of magnitude here that you get to play with if you're focusing on the dwarf galaxy regime. So what does this translate to in reality of simulations is that you get to go to way, way, way smaller structures. So even though you keep the large-scale cosmological framework that gives you a kind of a realistic merger history, you get to add these very small-scale things like a multi-phase ISM with individual giant molecular clouds. You can have individual star particles rather than single stellar population particles, as typical cosmological simulations would do. Which, of course, once you have individual stars, each star can have its own age and have individual chemical returns over its lifetime. As I mentioned, POP3 stars, so because now these ultra high resolution simulations are also very sensitive to their early evolution, you need to do the metal seeding more accurately than previously done. So that is included. Then individual supernovae explode, and we resolve the cooling radius of every single supernova within this whole galaxy. So you're really getting to like very small things. Of course, with every supernova, you get supernova-driven outflows, so you get a much more realistic circumgalactic medium. And lastly, one thing that sort of comes out of just going to higher resolution is that the star clusters form naturally. So clustered star formation happens just because of collapsing GMCs, as we would expect, but this wasn't always the case in previous simulations. So that's just the model overview. This is what some of the objects look like at redshift 0. This is surface brightness maps. And so there's currently only 5 simulations because I've only started running them this year. They're all in the mass range of 10 to the 9 or 5 times 10 to the 9 in halo mass, and they form between 10 to the 6 and 10 to the 7 in stellar mass. And I'm running all this at a 4 solar mass resolution for all the gas cells. So this is what they look like at redshift 0. And so one of the powers of simulations is you can go back and look at how that happened. So this is just a little video of only the luminous components of one of these halos as it forms. So they are all consistent with being dwarf spheroidals later on, but they're definitely not really that way at much higher redshift. Instead, they're just very wild, active systems merging out of many, many small and some larger systems. But through all of this merging, you get a kind of a dwarf spheroidal shape afterwards. We can go back even further in time and look at, for example, the metallicity as it's being distributed around the CGM and then even the IGM. So each of these little bubbles is one single seed mini halo that has a few stars and explodes with supernovae and distributes these into the medium, even growing in the final stages to one large enriched halo, where you wouldn't necessarily even be able to distinguish which parts of these are from individual halos anymore. What did the individual explosions look like? So this is 2 superbubbles from clustered supernovae within the simulations, one at redshift 8, where you have this kind of hourglass shape, one at redshift 4, where it's already probably more stuff has been going on, and so you get these very complex, but I would say beautiful bubble shapes in the gas density. So the first question that probably most people will ask is, what does the star formation history look like of these systems? So I'm plotting it here as a function of redshift, just because most of the activity is at high redshift. And so the gray band is reionization, hydrogen reionization happening. And as you can see, all 5 of the systems that I'm showing here have a truncated star formation history within that gray band. And then 3 of them have some amount of star formation at later times. And one thing that really struck me when I plotted this initially was that they each have kind of the same gap in this area here. And it's about 500 megayears, and so I was really interested in looking at this gap in more detail. Just to give you a look at what that gap during that time, so from pre-reionization, so reionization happens at redshift 7.8 here, so this is before reionization. This is a whole sort of mini filament where different little halos are forming, and then at redshift 7.8, when reionization happens, this is what's happening to the gas in this filament, is it's just being photo-heated by the background. And so this is the truncation that's happening in the star formation histories. But then, as we see, I hope in this video, if I haven't truncated it too far, at redshift 5 around, there's actually a tiny little core that ends up being able to form again and finally form some stars in the way center here. And so to look at this quantitatively, I've plotted here just the one history of one of the systems. Top plot is density, where the colored line is central density within 40 parsec, and the black line is the mean density of the entire halo. You have the cooling time as the colored line in the central plot, with the dynamical time in black, and then the bottom panel is the net flow rate across the virial radius boundary. So anything above the black line here will be net outflow, and below is net inflow. And I've just zoomed into the time just before reionization to reionization, which is the black dotted line, and then a little bit further on. And so the gray bands in the background are when star formation is active. So you can see that this central area is this odd truncation at reionization with this time until it restarts. So what we can start understanding is that, like, the central gas density drops at reionization, but then it's actually starting to rebuild itself already pretty much right away. It just takes 500 megayears for it to grow into a density that's high enough to restart forming stars. And the other thing we can point out is that initially at the time of reionization, what's happening, of course, is that all the gas is being suddenly heated, so there's a lot less inflows, and the net rate of flow across the virial radius boundary is all in outflows, possibly driven both by supernovae, but also just the lack of inflows. But then during this time in between, this whole thing turns around. So what's actually happening is the halo is sort of breathing. It's going out, expanding, and then it's just massive enough for it to bring this stuff back in and restart forming stars at that crucial moment. And then this is a bit too complicated to go into right now, but it's definitely, yeah, related to how we finally then come up with a baryon fraction for these dwarf galaxies. But I'm done anyway, so there's a weird humming. So just to finish off, Lyra is a project I've been working on to run ultra-high resolution dwarf galaxies. It probes the earliest luminous structure formation, and reionization has a dramatic effect on these systems, and we can learn a lot about the connection between the ISM and the CGM, or even the IGM, from this kind of simulation. Thank you.
Next, questions for Thales.
Thank you, Thales. This is a very impressive suite of simulations. And it's also, impressive that you can, in the simulation, you can resolve the giant molecular cloud. And my question is, so since you can resolve such detailed structures, so does the disruption of this cloud depends on your feedback processes? So do you consider, for example, early feedback, or do you rely on the supernovae to disrupt this dense material?
So the main feedback mechanism currently implemented in the model is supernovae. So that's definitely what's disrupting them currently. But yeah.
Okay.
I'm just wondering if we know that supermassive black holes form very early in the universe. Is there any chance for them to form here? Or, putting it a different way, what's the next major lever that you want to add to these simulations?
So
one of those questions.
There's definitely a lot of things that can be tested with these, and it's more than I can handle. But so early radiation from stars, especially pre-reionization. So yeah, the connection between, how many photons do dwarf galaxies actually contribute to the process of reionization? But then also, when you're modeling them properly within the simulation, do they truncate their own star formation earlier than like the general reionization would? So that would be one interesting point to look at. And then the other thing, the next lever, I guess, is more massive systems. So they're fairly expensive simulations. So I'm definitely have to push for what I'm hoping is kind of a SMC size system as one of my next goals, as the bigger ones.
I have a question online. So
we have a question from Rohan. What are the observable signatures of mergers that the dwarfs undergo? Are there chemical signatures?
Observable signatures of the mergers. I mean, I definitely think the stellar structure is, it's hard to, yeah. Like the fact that we see dwarf spheroidals at redshift 0, to me, seems like, from my simulations, it's fairly clear that dwarf spheroidal structure comes through like multiple mergers. So you lose a lot of phase-space information through these multiple mergers, and that's why you end up with this kind of more elliptical system. But chemically, well, there's definitely like a metallicity gradient within the systems. I didn't show it here, but that might be something to look into too.
One more question in the room?
So you mentioned that the redshift zero properties of your galaxies are in broadly good agreement with observations. So I'll use that as license to give you a little bit of a hard time about this. It seems like your final stellar masses are something like an order of magnitude above range of proposed abundance matching relations between stellar mass and halo mass. So is that cause for concern at all? And do you have any thoughts on why that might be?
So this is the stellar mass halo mass plot for my simulation. The only one that's truly out is the one red dot up at the top, depending on which extrapolation you assume. So I've added here the edge simulations as blue circles and Fire 2 as squares and Fire 3 as stars. There's definitely like 3 orders of magnitude in expected stellar mass, and we are on the upper end of that for sure. I'm currently not too worried because, as I mentioned, like the radiation from stars is highly expected to affect the star formation histories. So that would that's step 2 of this project. So I guess I'm not worried. But.
Okay, so let's thank Thales again for the time. Our last speaker is online remotely through Zoom, Rohan. He's going to tell us about the first glimpse of first galaxies. So you can share your screen. No.
Yeah, could you tell me if you can see the screen, if you can hear me, all the good stuff?
We can hear you, we can see you, we can see the screen.
Okay, that's great.
I will try to remind you 2 minutes before. So
okay, sounds good.
Sure, okay, let's take it away.
Yeah, hi everyone. My name's Rohan Naidu. I am a first-year Hubble Fellow who's just starting at MIT. I'm excited to talk to you today about the first glimpse of the first galaxies with JWST. Before I start, I want to say that the work I'm going to show you today was done in collaboration with a really collaborative, amazing team, and primarily with Pascal Usch. But one thing I want to highlight is that relevant to the conversation earlier today morning, a lot of my mentors, a lot of the people listed here were formerly Hubble Fellows. And so in many ways, this program has really shaped my scientific career by sending all these amazing, generous mentors and people who've helped me along over the years. So it's really quite an honor to be here today and talking to all of you as a Hubble Fellow myself. So let's start off with one of my favorite plots in all of astronomy. Which is a brief history of the universe. I love this figure just for the sheer amount of scope of space and time it contains in a few pixels. So all the way on the left over here, you have a depiction of the Big Bang. And so after the Big Bang, the universe is plunged into darkness. There's no stars or galaxies yet. And out of this ocean of neutral hydrogen, you have these first lights turn on. You see these first stars and galaxies then begin to blow ionized bubbles around them. These bubbles coalesce. And then finally, we have reionization complete. And then finally, today, we are sitting in a galaxy like this one, trying to figure out everything that has come before us and trying to make sense of it. So in this talk, I'm really going to focus on this very early epoch of the universe, this cosmic dawn epoch when the first starlight begins to emerge in the universe. And this really is our last major uncharted epoch of the universe, where we currently know only one galaxy that's been spectroscopically confirmed. And so a major goal of astronomy is to really like fill in these missing pages in these very early phases of the universe to figure out, where everything ultimately came from, where all these first stars and first galaxies that eventually would give rise to things like the sun. When did they first turn on? And one of the great privileges of working in this field is we can directly observe the early universe, because when you look at galaxies that are so distant, as shown in this very amazing video from a Japanese state broadcaster, you really are perceiving these very distant galaxies as if they were just very recently born, because of the sheer amount of time it takes the light from them to reach us. So we are still perceiving these galaxies in their infancy, even though they may be getting ready to file for retirement today. And of course, we are awash in photons from galaxies at all various stages of life simultaneously. But what is very helpful when we are searching for these very distant, very first galaxies is a couple of effects that let us really isolate them and hone in on them. So what's going on here, I'll show you in this figure, is a bunch of filters, a bunch of bandpass broadband filters that the Hubble Space Telescope uses. And I'm showing you the photons coming out of a galaxy. So this galaxy in this movie, we are going to set at a variety of redshifts, at a variety of distances, and we're going to see how its light behaves. And so there's a couple of things going on here. So when I play this movie and we set the same galaxy at various redshifts, you see that as you go to higher and higher redshifts, all the light from this galaxy is concentrated in the redmost bands. So we see this galaxy purely in the infrared. So at a redshift of about 11 or 12, this galaxy is detected purely at about 1.5 micron and in no other band. And what's going on here is because of redshift, of the expansion of the universe, combined with the fact that these very early galaxies are sitting around huge blankets of neutral hydrogen, what happens is all this bluer light is completely absorbed. And so the characteristic signature of these very distant, very first galaxies is that they're very well detected exclusively in these infrared bands, and not at all in all these other bluer bands. And so with Hubble, we really pushed Hubble to its brink, and the current most distant known galaxy that's been spectroscopically confirmed is at a redshift of about 11.1, really pushing Hubble to its very, very limits. And this is a galaxy that sits at about 400 million years after the Big Bang, is relatively massive. And the dream was always for JWST to push this forward, to look for even more distant galaxies by extending Hubble's coverage farther into the infrared. And that's exactly what JWST has done. So it's given us access for the very first time with such sensitive resolved photometry to the universe at wavelengths beyond 2 micron. Which is very important for all the reasons Ryan was discussing earlier, because this really marks kind of the limitation of our abilities with Hubble and also doing astronomy from the ground. And within the very first week of early JWST data with the ERS early release science programs that were all instantly made public, we found that, JWST was very much living up to this promise, the thing that it was built to do, which is push the cosmic frontier all the way to the Big Bang, was something that seemed very much in its reach. And so here I'm showing you an example of a galaxy very much like GNZ11, the current most distant galaxy known, where you see that it's detected in several bands. It's not just a single blip in one filter anymore. And it shows this characteristic drop-off of there being no photons whatsoever at these bluer wavelengths. And this exquisite data for the first time really lets us measure properties of these galaxies detected in these very first generations of galaxies that we are now detecting in several bands and measuring very precise redshifts for, deriving things like stellar masses. And what we were really surprised about was how easy it was for JWST to see these things. Within this first tranche of data already, we found these two extremely luminous galaxies that seem to sit at redshifts greater than 10. So this is a galaxy that we very creatively named GLASS Z11 because it was found thanks to the GLASS ERS program's data at a redshift close to 11. And another galaxy that we called, again, very creatively, GLASS Z13 at a redshift close to 13, which, if confirmed, would be the most distant starlight that we have ever perceived. And this was something that came at a time where within the first couple of weeks of JWST, it seemed that we were already living up to these dreams that had been in place for several decades, that several generations of astronomers had dedicated their entire careers to. And so it was very, it was quite an experience to see these images that we made on our computers just proliferate around the world, because it came at a time when all of us were, I guess, looking for good news among all the wars and the plagues, and it was just such a celebration that this sublime instrument was working and doing all these things that we were hoping it to do. This is my favorite piece of press coverage that came out of this period, where Captain America himself, Chris Evans, took an interest in our red blob and let his 15 million followers know about this. And since then, since this first week of really exhilarating discovery, we've had so many other redshift greater than 10 galaxy candidates also be reported. But for the rest of this talk, in my couple of minutes, I'm just going to focus on some implications from some of these two really bright galaxies that not only us, but several other teams have also since placed at these very distant redshifts. One early surprise is that there seem to be many more bright galaxies than some of our simple models suggest. So if you take your standard Schechter luminosity functions, your UV luminosity functions, which basically tell you what number of galaxies you expect as a function of brightness, we see that we are finding an order of magnitude more bright galaxies than you would expect from these simple luminosity functions. So this is shaping up to be a pretty exciting mystery of what is driving this remarkable abundance of very early and very bright galaxies. The community has come up with several answers, and it could do with the very early initial mass function of these very first generations of stars. It could do with primordial black holes. Maybe dust is behaving differently at very early times. Another early surprise has been with how some of these systems might be in tension with lambda CDM cosmology, which boils down to, if we convert these remarkable luminosities into stellar masses, then we run into a problem where we are unable to find dark matter halos to fit all these stars into. This is something that folks have called the too big to be problem, which is that within standard assumptions under lambda CDM cosmology, like galaxies that are so massive are in tension with existing so early. So this is a plot of redshift, and here we are showing some version of what the maximum stellar mass is allowed at these epochs with various occurrence rates. And so this is potentially something very exciting if more and more of these systems end up being confirmed. I'll quickly end with what are we doing now? The really major
one minute.
Yes. Yep, got it. the really major next step that we need to do to go from these being galaxy candidates to being confirmed galaxies at these very high redshifts is to explore spectroscopy. So we really want to measure these galaxies with spectral emission lines, or we want to measure breaks. So we've already started doing this with ALMA, some first steps, where one of these galaxies was recently observed. And we found that at a wavelength regime where you would expect oxygen emission that Ryan was talking about earlier, we see nothing, which is telling us that this galaxy, if it is at this redshift, is potentially quite metal poor. And the other system that I presented is also excitingly in queue to be observed very soon, this month potentially. We can also use JWST for spectroscopy to confirm these systems. So the feature that we'll go after there is measuring this very sharp Lyman break feature, where you suddenly see flux and then it goes to zero with this very sharp edge, which is a smoking gun signal of absorption due to neutral hydrogen around these very early galaxies. And a whole variety of potential lower redshift interlopers would produce a much smoother drop-off in their flux profile. So this would be very distinguishing. We might also potentially detect like very bright rest UV lines, things like helium-2 that people have posited might be very bright in the first generations of stars. But yeah, we really need spectroscopy with JWST to confirm this. Yeah, that's what I've got for you today, and I'm very happy to take questions.
So, question. Hey, Rohan, Ryan here. Nice talk. Really enjoyed it. So in the past few weeks, the NIRCam 0 points have changed, been fairly flexible. Have you done any looking at how your SED fits in the infrared galaxy masses might have wiggled around because of that?
Yeah, so that's something we're really actively working on, and that is something we also were aware of when we were writing these papers, honestly. Like right away, it was clear from some of the early fits that the 0 points could move around. And that's why, at least in our work, we limited ourselves to galaxies that were so luminous that the strengths of these breaks would protect them even if the 0 points moved around by 20, 30, 40%. So that's that on in terms of like their being like, whether these are dropout galaxies at these redshifts or not is fairly like inured to that particular question in terms of 0 points. But indeed, the masses could move for sure, and that's something we're working on right now. As you know, like this, even the corrections to the corrected 0 points are currently in flux. With different answers depending on which calibrator you use and so on. So yeah, that's definitely something we are going to update in the revised versions of these papers, redo all the stellar masses and such.
Other questions online?
There are no questions online, but I do have my own question, if that's okay. Rohan, can you go back 2 slides, please?
Yeah.
Oh no, maybe it was one more. You had an upper limit on the expected metallicity, and you said it was less than 20% solar. That seems high to me. So can you comment on that? Why 20%?
Yeah, it really has to do with the upper limit on the emission line flux that you can place, and the issue with ALMA is that when you're scanning. Not issue, but ALMA is such a blessing that we can even do this science, is that when you're scanning across all these various band passes, because you don't know the redshift, you can't go super deep on any single one of them. And so that limit's really coming from like how strong we can place the upper limit on the emission line fluxes, and then you convert it based on certain grids of models and such. So what's good about this observation is the fact that you don't see anything already like rules out like an entire class of very dusty, lower redshift interlopers and such. But it's also a bit frustrating because we just wish we would detect the line, right? But the line is, again, sensitive. It's telling you something about the abundance in these galaxies. So if you went deeper, you would get a better limit, basically, or a fainter line, perhaps.
So let's thank Rohan and all the speakers. We can, and of course, you are welcome to continue the discussion over Slack. And
okay. I'm hoping that Massimo Schiavelli, who's giving the first tour, will be coming down here. If he isn't here in a couple of minutes, I'll take you up to the mock, the people who are on the first tour. Oh yeah. So yep. Is Massimo here? Oh, Scott, you're going to do this one. Okay. So Scott Friedman over there. On the first floor, he's going Scott, and you'll head up next.